Okay, so I think things are live now. How are you doing?
I'm pretty good, all things told. Yeah.
Okay,
What you?
uh, doing all right. I mean, as I said, had a little bit of water getting into my place last night. We had rain on frozen
Yeah, it
ground,
is.
etc. So
Right. Yeah, it was just snow up here, but I was down actually. I was down at Lisa's parents, so we are getting a little bit of rain there. Pretty, pretty parallel to you. Same, more or less same latitude, I think.
yeah, yeah. Alrighty.
But
So yeah, you may want to maximize this just to like minimize lag, or I mean, actually
yeah,
maximize a new window, right? Like or something. And maybe open that file that we were putting things into last time.
um, wait, the you want to start from our last session? You're saying?
Yeah, not the REPL session, but remember we were actually saving stuff in a file.
Yeah,
Yeah,
yeah.
the top window.
This
Yeah.
is the
Okay.
file.
Okay. Yep. This looks good. So,
But this is the thing. It's just the file. It doesn't have the REPL.
what happens if you click? What happens if you click run? Yeah. There
Oh
you
yeah,
go.
nice.
Alrighty. Um. Okay. And just to make me sort of happy, I'm a little bit weird about formatting. It kind of hurts my eyes. Can we put a line of white space between lines one and two?
Between what lines one and two?
Yeah. Yeah, there we go. It just looks a little nicer. Kind of bothers me to have like definitions just start right there, jammed up against it. Um,
Alright.
okay, so last time we were talking about recursion, and
Yeah.
we should probably pick back up there and do a little bit of refreshing of memory on that. How is your recollection of what we were doing?
I think pretty good. I was listening to some of it. I didn't go back over the lesson, but I listened to some of it to the session. Um, and I did get there. I remember that moment of being like, oh yeah, two branches, and if x equals zero, then return one. Um, and it just kept not equaling zero, but then eventually it equals zero as the base case.
The
Is that
base
it?
case. Yep.
Um, and then you can go back through and it performs all the calculations in the factorial. And then I did kind of realize something on this, that factorial really is just, I mean, it's a term, but in this case, it's a mathematical term or function or whatever outside of coding. I think is what you were telling me. A factorial of a number, but
Yep.
in this case, it's the name that's bound to this procedure.
Right. It is the procedure itself, which is
Yeah.
sort of the point of you know
Naming it.
the
Yeah.
recursive procedures. And there is a distinction between recursive procedures and recursive processes, which we'll talk about eventually. This is both. This is both a recursive procedure and a recursive process.
Uh-huh.
But what makes it a recursive procedure is basically just the fact that it calls itself, right? Factorial
Mhm.
calls itself. And so the thing is, if you have a procedure that calls itself, one of the things that's very important is that you do have a base case and that every invocation of the procedure gets you closer to the base case, right? Because otherwise it will
Yeah.
just call itself forever, right?
Yep. Yep.
And that you generally don't want. So let's take a look. So we have factorial here. And, factorial is a really classic. I don't know if it's actually even the best example of recursion. One of the things about it that's really silly is that factorial actually has a closed form solution, right? You can just write factorial down as a single, very simple calculation. So you would never actually write factorial this way. But it's a pretty good example. I actually had a job interview a few years back where this was sort of the first thing they asked me was, can you write factorial? And I think they were expecting the recursive solution, so I gave it to them.
Uh-huh.
But so it's a bit of a chestnut, right? This is often where people begin explaining recursion.
Hmm.
And we have another example here, which is we named this recur length because there already is, the name length is already bound to a procedure in Racket,
Yep.
right? So we don't want to step on that. But you see how this works here, right? We're looking for the length of a list.
Yeah, and you're using the rest to add one to the, now let's see, to the rest of the length of the, not the rest of the list, but the rest of the length of the list. So it's like translating it to
It's
numbers.
it's not the rest of the length of the list. It's the length of the rest of the list.
Thank you. Yeah.
Right, because that's actually really, that is one way of defining the length of a list, right? We just say, what is the length of a list? Well, it's 1 plus the length of the rest of the list, because the rest of the list has a length that is 1 less than the length of the list, right?
And length is, it will be expressed in a number. So, I mean, we're dealing with numbers here again. I mean, I guess it all, it's translated into numbers.
I mean, it just is numbers. That's what this procedure returns, is a number.
Yeah.
You can look at both branches. You can see, okay, the first branch of the if returns a number, and the second branch of the if returns a number. So it always returns a number. And we've talked a little bit briefly. It's something I will bring back up again, though. So we've talked a little bit about types, right? Because different things in Racket have different types, and Racket is dynamically typed, so you don't have to tell it ahead of time what the types are. It pretty much just sort of looks at things and figures that out. It knows what the type of things are. But functions themselves can be thought of as having types, right? And the type of a function is a combination of the types of its arguments and the type of its return value, right? So we wrote a function square that squares a number, and that's type is basically, we can say that its type is essentially that it is a function that takes a number and returns a number, right? And so it's good to really think about that kind of thing. A lot of the time, it really makes things clear. And so you kind of have to know that, because look at this. We're saying 1 plus and then calling recur length on rest of list. This only makes sense if we know that recur length returns numbers, right?
The same type.
Right. If recur length could return something else, then this wouldn't make sense, because you have to, because plus is basically only defined on numbers. And there are some languages where that's not entirely true. Like in a lot of languages, actually, you can also add 2 strings together, and it will just sort of concatenate the strings. But Racket is a little bit stricter about that. Racket is a little bit more strongly typed than that, basically, and it's it has a different function for concatenating strings. But for instance, Python and Python will blow up if you try to add a number to a string, because it's like, I don't know how to do that. JavaScript, though, which is actually very weakly typed in some respects, JavaScript will very happily add a number to a string, and I think what it does, it's a little hard for me to remember because you should pretty much never do this. I think what it does, though, is it actually turns the number into a string and then concatenates the string representation of the number with the string. So, and we will start looking at some other languages at some point. So, it's good to understand that this is not universally true. Some languages do overload operators. They allow operators to work on more than one thing, and they do different things depending on what types of things they're working on. But Racket,
and this, the quote there, that defines a string, or is that that's probably not the right term?
Well, double quotes are, when you put things between double quotes, that is a literal representation of a string. So if you want to just enter a string, you just put some characters between double quotes. So if down in the REPL you just type in double quote, hi there, and double quote, right?
It'll just return it with the double quotes.
Right. Yeah, it's just printing it for you, and it prints the double quotes so that you know that it's a string, so that you can see that it's a string.
Right.
And also because typically when the REPL prints things, it prints them in a form that it would be able to read and get the same value. There are no double quotes. There are no double quotes in this string, though, right? The double quotes just indicate that this is a string.
Gotcha. Yeah, string start, or start string, string, end string. Kind of like the double quotes.
Yeah.
Indicating the start at the end. Yeah.
Pretty much. And you can see up there where we have that procedure up at the top where where we have print lines. The number was off, the number was even. And again, those are just strings. And strings are distinct from symbols.
Yeah.
So symbols are like factorial, for instance, is a symbol, and we have bound a value to that symbol. Strings are not symbols. They're a different thing. You can turn symbols into strings, and you can turn strings into symbols. But they are different types, and they're very different in a lot of their characteristics. So, getting back to recursion, though, so trying to think of another good example of this that doesn't add a great deal of complexity to what we're doing. Here's an interesting thing, and of course, this is a little silly in Racket because Racket's plus already works like this, right? We've talked about this how plus in Racket, you can add more than two numbers with plus, right? You can go plus 4, 6, 7, 8 if you want to. But let's think about writing a procedure called sum that takes a list of numbers and returns the sum of all of the numbers in that list.
Okay.
So let's think about the function's type first, right? What type is this function going to have?
Additive type.
Okay, but we were just talking about this, right? The type of a procedure is really basically composed of the types of what it takes as arguments and the type of its return value.
Oh, okay. So its type is it takes a list of numbers and returns a value.
And returns a number.
Returns a number.
Yeah.
Right. A value.
So you want to bear that in mind as we're going along. So do you think you want to try to take a stab at it? I mean, this may be, I know that, we kind of just started touching on recursion last time, so this may be kind of tricky, but why don't you take a stab at it and see how far you get?
And I can use, isn't sum already defined in, and I don't want to use sum as the...
Actually, you could type it in at the REPL and see if the name is currently in the space. Just type it in at the REPL. I think it's going to be unbound. Yeah. I mean, you don't need it in Racket because plus already does that in Racket. The plus sign, right? Yeah. There are languages with a sum because if you do infix arithmetic, that is to say, if you put the plus sign between numbers, obviously it can only operate on two numbers. So you need a separate procedure to do sums, for instance. Python, for instance, has a sum procedure, but you just don't need it in Racket because plus can already, we're just replicating some... We're replicating some functionality here that Racket already has. Okay. So can I ask why you are naming that argument list sum? I'm just curious.
I don't know. That just seemed like the most intuitive.
Okay. I would probably just name it LST. Yeah.
Oh, okay.
Because there's not too much reason for the sum to be on the name there. But
okay, so... What do I want to add?
So let's think about this for a second, because there is kind of a trick to this, which we've touched on, but I want to kind of mention it again, which is we want to think about how we can define this in terms of itself. And usually with lists, that means defining things, in terms of the first thing in the list and the rest of the list. That's with recursive procedures that work on lists, that's an extremely common pattern.
Yeah, makes sense. So if I got a list of 4 integers, and I want to I'm going to add them together one at a time, more or less. I mean, this is just kind of the way to think about it. But then what would a base case, but I'm not adding one necessarily. I'm just adding I'm going to be adding the first of it to the, I could add the first to the rest if I started with the,
well, what's your base case here?
An empty list.
An empty list. Okay. Now, what do you think the sort of sum of an empty list ought to be?
0.
Okay. That seems pretty reasonable.
Yeah. So I guess it would be it. Oh, it's the same thing up there. I wanted to do that.
Okay. Yeah, but it's LST. Because list is a name that we don't want to stomp on.
Right. Yeah. That was actually. Now here, I'm not adding one because the list to integers could be all over the place. I need to add. I mean, I think I'm adding just the. First. First each time. How's it gonna? I mean, I can't. I'm not.
You're very close. You're very close. What you're saying is, like, what I hear you saying is so far basically the right thing. So let's think about this. If we want to define the sum of a list of numbers in terms of, and this is kind of the trick with this, we want to define it in terms of the first thing in the list, and then the result of calling the function that is our recursive function on the rest of the list. That's typically how a lot of recursion on lists look, right? So we want to define the sum of a list of numbers in terms of the first number in the list and the sum of the rest of the numbers in the list. What would that definition be? Just sort of in English. Don't worry too much about the code, but just conceptually, what is that?
Just, I mean, be adding up the rest of the list. I mean,
well, okay, but here's the thing, and this is sort of one of the tricks with recursion, is that there's a recursive call, and with lists, it's very often going to involve recursing on the cooter of the list, right? On the rest of the list. So we just assume that does the right thing.
Yeah.
Right? Like, we just assume that the recursive call does the right thing. We don't really try to think about what it's doing. We just say, that does the right thing. And now, and that's kind of the trick. That's the tricky bit with recursion, is making that leap of faith and saying, I'm just going to assume that if I call sum on the rest of this list, sum does what it says, right? I don't even have to think about it. It just does what it says. It sums up the rest of the list. So if I know that, how do I express this in terms of the first thing in the list and the sum of the rest of the list?
I mean, I don't know. I can't really quite think it through, but it seems like it would be.
Okay, it's not quite there. So you're very close in some ways, but what you really want to do, let's think about this definition. The definition of the sum expressed in terms of this is the first number in the list plus the sum of the rest of the list. Of the rest of the numbers in the list, right? So let's say we have the list like 3, 4, 5, right? So the sum of the rest of the list is going to be 9, right?
Yep.
The rest of the list is a list containing 4, 5. So what's the sum of 3, 4, 5? Expressed in terms of the sum of the rest of the list.
3 plus 9.
3 plus 9. So we just have to add the first thing in the list with the sum of the rest of the list.
Oh, I don't.
So do you see that line up there where we're adding 1?
Why did I do that? Yeah.
In recur length. If you replace that 1 with first list And then you just sort of replace the recursive call recur length with a recursive call to sum. Just replace the name. That's what we're recursing on. You'll get what you want here.
Okay.
This is actually very similar to the length. Right. But first is a procedure. So how do you... So first of all, we want to add two things together, right? That's what we're doing here, is adding two things together.
Oh, right. Yeah.
Okay. Yeah. And then first is a procedure, right? So how do we apply a procedure to an argument?
Yeah.
Yep. But you do also have to close that procedure call, right? Yep. And now you probably want to check your parens.
Oh.
Yeah. Looks like you may have one too many. But that starts to look, yeah, something a little bit weird's happening there. I might pull the screen like down just a little bit, pull the divider down slightly, because it keeps like, okay, yeah, that's probably pretty good. It keeps kind of stomping on that. I mean, Dr. Racket is not necessarily the best editing environment in the world. It's just very, very simple to set up, and I haven't wanted to talk about setting up an editor for you yet. And it's good enough for our purposes right now, but it can be a little bit of a pain. So yeah, that looks pretty good. Why don't you hit run? Okay. So, oh, it doesn't quite look good, actually. So let's look at that last thing, sum rest of list. How many arguments does sum take?
2.
No. Let's think about the type of sum. We just talked about this, right? So what is the type of sum? What does this take? How many arguments does it take? What are the arguments that it takes?
Sum is, well, yeah, with one argument, it's adding.
It takes one argument. It takes a list of numbers, right?
Yep.
Sum takes a list of numbers and it returns a number. So let's look at that last little bit in the last line where you have sum rest list. So when you have a procedure, when you apply a procedure using an open paren, right? And then you have the name of the procedure, it applies it to the rest of the things within those parentheses, right? So you have two things inside the parentheses, rest and list. Okay, but you don't want to just send it list, because if you do, it's going to run forever, right? You aren't getting any closer to the base case if you pass it in the same list.
But if I put I guess because sum already knows it's talking about a list, so I was like, how is it going to know?
It's not that it knows that. It doesn't know that it's talking about a list, right? Some,
Well, okay, it knows it, right? It knows that we're talking about the variable LST.
Right. LST is a name that gets bound. When you call sum, you pass it one single thing, and that thing will be bound to the name LST in the body of the procedure, right? That's just pretty much how procedure definition works, right? Is that the things you pass as arguments get bound to the names in the argument list. So the issue here with what you were doing before is you were just missing some parens. What you need to do is apply rest to list to get the rest of the list, right? No, okay. You do need to tell rest. It does not know. I mean, you do need to give rest an argument. How many arguments does rest take?
1.
1, which is a list. So you need to give rest a list as an argument. But you need to actually apply rest to that argument, right? How do you apply a function to an argument?
Open paren.
Right. So you need to apply rest to list, right?
Oh.
Okay, but it's LST.
Whoops.
And now you want to check your parens just to make sure they all balance, etc. Like I would just go to the end of there. I have a feeling you may be missing one. Yeah, there you go. Right. So what you had before was like this, except you didn't have the parens around rest LST,
Yes.
right?
Right.
So you were passing some two arguments, one of which is the procedure rest, and one of which is the actual list you have here. So that would have blown up because sum only takes one argument.
Yeah. Gotcha. Would have been an error.
Yeah, it would have blown up. It wouldn't have run forever. However, if you just passed some list, LST, if you just passed some list, it would run forever, right? Because there's no point at which you are getting closer to the base case there, right? You just keep passing it in the same list over and over again. So that's never going to be empty, right?
Yeah, because it's the same thing.
It's the same thing. You're just not getting closer to the base case. All right, why don't you try running this, and let's see what happens.
Now I need to do a list.
You need to make a list, and there's a couple of different ways of doing this, right?
I have to put that little.
Okay. So you need to do one or the other. Let's just go over a couple of things. Let's just refresh our memory about a couple of things here. So if you just back up, we'll just do this in the REPL. Just backspace over what you have. Okay. So one way of making lists is to use the list function, the list procedure. Okay.
And you don't need any.
You don't need a quote there. You just have a list, and then you give it some arguments, and it will be a list of those arguments, right? Yeah. Exactly.
Okay.
The other way to do it is basically what it just returned to you right there is readable, and that's so if you type in basically exactly that, right, you'll also get that out. Now there are a couple of gotchas about using the quote, and what's important to remember is that it basically winds up quoting everything inside the list as well. I made a mistake about that a couple of sessions ago, if you recall, which was pretty embarrassing. I had totally spaced that out. For this kind of thing, though, we don't really care, right? That's fine.
Okay.
So you can do either of those when you call some.
Okay. All right, it worked.
And it worked. Yeah. So let's really take a look at this. So you got the base case right away, right? Which is good. And that's kind of the first thing you need to think about when you write recursive functions is what's the base case here? What are we trying to get closer to, and what is going to be the definition of that? And when you are recursing uncooters, this is a particular pattern that's very common in Lisp, and it's called it's cooter recursion, recursing uncooters. Which is this thing where the recursive call takes the rest of the list, right? When you are doing that, the base case is almost always, the base case is always, that's kind of the definition of what we're talking about here in that case, is always is pretty much always the empty list. Now, you could have gotten a little bit fancier about this base case. You could also have said, you could have had a condition that checked to see if there was only one item left in the list, and returned that item instead of 0. Do you see that would work?
It stops the loop, but it still keeps the value to then add.
Well, you could have a different base case. Instead of an empty list, you could have a base case of a list of one item, right? Well, what's the sum of a list of one item?
Yeah, gotcha.
That one item, right? But that just makes the code more complicated. It's also in some ways less. There's something sort of very neat about this definition of just saying, yeah, the empty list has a sum of 0, right? Which may seem a little bit funny to even talk about the sum of an empty list, but it actually, that makes sense. So this is a really common pattern, right? So when you're doing recursion on cooter, clearly you can do recursion, you can do stuff that's not recursing on cooters. Factorial doesn't, for instance. Factorial, there's no list involved here, right?
Yeah. Right. Just counting down.
Yeah.
Or it's just, yeah.
Yeah, you're just counting down.
Yeah. The list, I guess, is already established as the integers, but.
Yeah, it's not a list, really. It's not a list. You just, this is a function that takes a number and returns a number, right?
Mm-hmm.
But it is very, very common to want to recurse on lists. That's a very, very common thing to do. And when you do, typically the empty list is your base case, and you just have to have a reasonable definition for what this procedure should return when it's applied to the empty list. And in this case, we do. It's 0. So that's sort of the first part of this pattern, is the base case. The second part of it is pretty much always some way of combining the first thing of the list with the result of calling the procedure, of applying this procedure to the rest of the list.
Yeah.
Right? And it pretty much always looks like this. And you can see recur length has exactly the same pattern, right? It's just a question of how you combine the two things. What's the combination of these two things? And in both these cases, it's an addition, but it doesn't have to be an addition. It could be some other method of combining them, right?
Yeah, you're right. Yeah.
Okay. And you'll note that things in these cases that we've looked at right now, we're always taking lists and we're essentially reducing them. This is a reduction in the sense that we take a list and we turn it into a single value, right? It sort of compacts the list down.
Mm-hmm. Okay.
Right, into one thing. And indeed, there are some procedures that we'll take a look at that kind of embody this kind of thing. Not even necessarily just with lists, although that's very, very common, but reductions, folds, basically, are what they're called. And they kind of embody this, and you can use them to avoid having to write the recursion out. And we will take a look at folds, probably fairly soon. But not every recursive procedure is going to do that. Some of them will not reduce the size of things. So there's some other ones. So one that I would like to take a look at now is, let's think about this. Which do we want to do? How about we take a look at map first? So do you remember map? We've seen map.
Yeah. We didn't look at it too much, but we looked at it some, like 2 or 3 times ago. It was like map. It was, I think, or we did something like map plus 2 onto, and then it was a list, and then it added 2 to everything in the list of integers.
That's exactly right. And we kind of looked at the fact that there is a slightly more complicated, like, use case. Map can take more than one list, but we're going to concern ourselves right now with the case where map just takes a single list. So this is a somewhat limited version of map, because we're going to write our own version of map. But we're not going to try to deal with multiple lists. We're just going to say, okay, map takes one list. So what map takes is a procedure and a list, and it returns a list that is the result of applying that procedure to each item in the list that it got, right? So why don't we define a function that squares things, right? We've done this before. Call it mySquare. There is no square in your environment right now, but we're going to want to use a library at some point that actually has square as a name, and I just sort of know that. So let's just not pollute things, let's be careful about,
yeah.
Square. And that is not actually how you spell square. I think you just typed it. I think you know that one, yeah.
Well, I didn't see it, so.
Yeah.
So we're just starting out with actually just doing the math function square.
Yeah, it's just going to be convenient to have it around as something to map across this. There are some other things we could too, but we'll use our own. Okay, so why don't you hit run and just test mySquare out? Let's make sure mySquare works. Yeah.
Good.
Okay. So that looks pretty good. So try mapping mySquare across a list of numbers. I mean, you can just do it at the REPL. I don't think you don't really need to save this, but we just want to take a look at how this works. Okay. So what does that error message look like it's telling you?
The number of arguments do not match the number of given number specified. Need at least two. So it's saying, okay. Oh, whoops. What did I? Oh, I never put my mind square in.
Okay, so that looks pretty good. So now we want to write our own map. So maybe we want to call it my map or something. Right. So let's think about this. What is sort of the type of my map? What's its? People sometimes talk about type signatures too. That's a word that you'll hear. What type is my map? The my map procedure that
Map.
you want to define.
It's a procedure that takes a list.
It takes
Takes a well, could it? Because it could take any. Okay, so it takes a given procedure.
a procedure, right? We're not interested in the concrete. When we talk about like these types and stuff, we're not interested in the concrete values of the arguments. We're just interested in their types.
Okay. So it's a procedure that takes a procedure, applies it to a list, and returns a list.
Right. It takes a procedure and a list.
Right.
Right?
Okay.
It's a procedure of two arguments, and those arguments are a procedure and a list, and it returns a list. And this kind of thing of thinking through the types of your functions, sort of like that's the first thing that you kind of need to do when you sit down to write a procedure is sort of know what does this take, what does it return. That's really when you define procedures. That's the first thing you should think, and then you should think about what good names for the arguments would be. And that gets you like quite a ways into writing the procedure, just doing that.
Okay. All right. So we're calling it my map. And it's going to take a procedure.
Yeah, you can
And
just call that PROC if you wanted to. Proc, that's a pretty common conventional name for a procedure.
ROC, you said?
Yep.
And a list. Yeah?
Yep, that's exactly right. Now, what's our base case?
Procedure will continue. It'll be, I think, would think empty list again.
Okay. And what is the result of mapping a procedure over an empty list?
Well, I mean, if it's a procedure that I'm thinking about, like a, oh, well, no, I guess it would be,
So what's the return type of my map? What type of thing does it return?
it returns a list.
It does. What list do you think, if we map a procedure across an empty list, what is the list that you think that ought to be?
Should be an empty list. It's got nothing to work with.
Exactly. Yeah, that's your base case.
So it's if the list is empty. But now is it going to be zero?
What do we say? I mean, so what type does my map return?
A list.
It
A
does.
list.
It does. So we know it has to be a list. And really what we want to be is like, what is the result of applying my map to the empty list? What is the result of mapping a procedure to across an empty list?
Another empty list. So
Another
I'm
empty
going
list.
to
So that's what you should return. Yep.
do I have to?
Yep. Quote, open paren, close paren is, yeah.
Oh.
One way of
Yep.
writing it. There's a couple ways of writing it, but that's a very common one. Okay. And now we have to figure out how to actually do the work here, right?
Mhm.
So let's think about this. We talked about recursion on cooters, right? And so we kind of know that if we're following this pattern, right, that
Yeah.
we're going to be combining some expression involving the first thing in the list with the result of applying my map to the rest of the list. So what we really kind of need to know is, how do we combine them? What's the combination operator? When we were working with numbers, for instance, we were using addition. And then we also kind of have to know what we're doing to the first thing in the list. And we didn't really see doing anything to the first thing in the list, operating on it above, except in the very trivial sense of turning it into one, right? We did kind of, in some sense, operate on things in that way. But let's think about this. What's our procedure? What is
I mean, the procedure, we don't necessarily want to, pin it down or whatever. We want to be able to have it be any number of different types of procedures.
Sure. So the procedure itself, we don't really care about. But, well, we do, in a sense. We don't care what the procedure itself is.
Yeah. We don't want to define it in this procedure.
Yeah. So this one is a little bit tricky. So, first of all, we need a combination operator, a way that combines things, so that we combine the result of doing something to the first thing in the list with the result of calling my map on the rest of the list. Is that kind of clear?
Yeah. And wasn't that a con?
Cons. Cons is going to be the combination. That's exactly right. So we want to so you can actually probably start writing this line at the moment, right? You can look up above and you can see our combination operator up above was plus. Yeah. You can see it's the same pattern, right? It's the first thing that's happening. The combination is the first thing that's happening.
Yep.
Now let's okay.
But it's the first of combine the first. It's would. Where is the procedure gonna? I guess it doesn't. Yeah, I don't know. I'm trying to. Maybe I should try to imagine how you would even apply it. As if we go to working backwards.
Well, what do we want to apply procedure to?
We want to apply procedure to the list.
To the list?
Because that's what map. Isn't that what we're trying to do? We're trying to.
Does map apply the procedure to the list itself? It doesn't. It applies the procedure to the things in the list. Right?
Okay.
So think about square. Think about square, for instance. We mapped my square over a list containing 2, 4, and 5. Does it make sense to square a list?
Right. I see.
What would the result of squaring a list be?
You'd have to do something. Yeah.
It only makes sense to apply square to the items in a list, and this does, by the way, imply that the list itself has to have items that are of a type that you can apply square to, right? So when you call map my square on a list, that list, part actually of sort of the type of that expression is that you happen to know that list has to have numbers in it.
Well, for my square. Yeah.
If you are passing my square to map, right? If map were something that operated on strings, you would have to pass it a list of strings, right?
Yeah, which this my map could potentially do.
That's right. We don't know what the type of the list of the things in the list is going to be, and we don't know what the type of the procedure is going to be. What we do have to assume, though, is that the procedure is going to take an argument of the same type as the items in the list, right? Just like when you call map my square on list 2, 4, 5, my square takes numbers, therefore the list that you are passing it is the second argument there. Do you see how it has to match? The procedure's type has to map the types of the items in the list. Okay. So
putting together.
So we can think about this definitionally. How would we define this in terms of some expression involving the first thing in the list and the result of making the recursive call?
last, and then it would be, I think it would be cons again.
Well, we're definitely consing, right?
Yeah.
We're consing something on. So let's think about what the recursive call does, okay? And remember, there's this bit where this is the leap of faith part. We just assume that the recursive call does what it's supposed to do, right? So what are we going to get from the recursive call? Maybe you should write out the recursive call. We know we're going to be consing two things together, right? That's how cons work. Cons, right? So maybe write out the second thing that you're consing, which is going to be the result of the recursive call. Write out the recursive call, just right here, right?
Nope. To get my fingers in there.
Yep. Yeah, that's the recursive call. So what is that going to be?
What is it going to be? What is my map?
Rest of list. What is that going to return?
It is going to return a procedure applied to each item in the rest of the list.
Right. It's going to return a list where, right, the procedure has been applied to each item in the rest of the list. Right.
Yeah.
It's going to return, a list of the results of those things. Okay. So how can we define what we want in terms of that and consing? What do we have to cons onto that list to get the result we actually want?
The procedure applied to the first item in the list.
That is exactly right.
Okay, and I need to have it in.
So yeah, this is just sort of about the mechanics of scheme. So we know we want to operate on the first thing in the list, and you've started writing that out. So just finish writing that out so that you have balanced parens, right? Close the parens. Now, if you were to go finish up closing your parens here, because I don't think you have closed all your parens at this point.
Yeah.
If you were to do that, this would be a runnable function right now. What would it actually return if you ran this? It's not correct. It doesn't do what we want. But what would it return if you were to run this procedure right now, assuming you had closed up your parens?
It would just return you the list.
It would return you exactly, right, the list that you had passed in. Right, exactly. Yeah. So we don't want to do that, but you were saying before, right, that about this definition, you said it exactly what it was, which is we want to cons the result of applying procedure to the first thing on the list. So how do we do that? This is just some mechanics. No, we don't need another cons, right? We already have the cons, right?
Right.
We don't need another cons. We just need to apply the procedure to the first thing, apply procedure proc to the first thing on the list. Okay. How do you apply procedures to arguments?
Well, but the proc, how does it know that the proc is, because it's, no, it doesn't know it's a map.
Well, proc's not a map. Proc is a procedure.
No, I know, but
How do you apply a procedure to arguments?
You you open parens, list the procedure, and then list the argument.
Well, you open a paren, right? The first thing after that open paren is your procedure, something that evaluates to your procedure. And then the rest of the things in the parentheses are what you want to apply it to. So what do you want to apply it to?
I want to apply this procedure to the first of the list. But why am I?
You've already written out first of list, right?
Yeah.
So
it's in place.
You probably want to go before first of list, right?
Yeah. But wait, that'll be two.
So first of list, right? You want to go outside these parens. You can think of that first list thing as just being a single value at this point. That's going to evaluate to the first thing in the list, right? Very close, but how do you, we want to apply proc.
Right, it's going to be a procedure.
There you go.
But then I'm going to need.
Actually, all you need to do now is close parens. So go.
I don't need to close them inside of the.
Well, you do. You don't need to click. You do need an extra paren after first of list, right? You're applying procedure to some things. So exactly. Yeah, we may want to like actually just take a little bit more of a look at just the basic mechanics of some of that stuff, because it's like you're getting the conceptual thing here really easily, which is something that a lot of people find quite difficult. Like I'll just say you've really gotten this stuff like quite quickly. A lot of people really struggle with this, but you're struggling a little bit just with like the syntax of it.
Yeah.
So I think if you had the syntax down, this would all really come. I mean, you're definitely like you're getting this quite well, right? So yeah, why don't you try running it and hitting run, and then try mapping my square across it. A list.
Wait. What were you gonna say? Try mapping what?
My square, right? We have this function my square.
Yeah.
Right. Procedure. Try mapping that across a list using my map.
Wait a second. Oh.
So it's going to have exactly the same syntax that map had when we did it. It's just we're using our version instead of their version.
Gotcha. And my square is already defined in that. I don't need to. Yeah.
Okay, this does need to be a list though, right? You're just passing it.
Yeah, I forgot. Yeah.
Okay, you still need parens to make the list though, right? You just quoted a 3, right? You want to quote a single thing. Quote works on a single value. It can be a compound value, which this is, but it is a single value. Okay.
The quote's got to be inside. Oh.
So this is right. There is one more thing that we're missing, which is what is the signature of my map? What does my map take as arguments?
Takes a procedure and a
list. And so when you're making your recursive call here with my map, how many arguments are you passing it?
I need to pass it 2.
You need to pass it 2, and you're currently passing it 1.
Isn't my square the procedure and then the other one's the list?
Well, when you first called it, yes, but then you got down to this line where you're making your recursive call. I mean, you actually have to edit my map. The definition of my map is wrong. Is what I'm saying. Okay, there's an error in here. So let's take a look there at where the error happened, though, right? On this last line of my map, you're calling my map itself.
Yep.
And you're calling it with a single argument, which is a list. You actually need to be calling it with 2 arguments, right? One of which is a procedure and one is a list. So this is the argument that is the procedure. How do we refer to the procedure inside this function?
It's got the parens there. Do I need my map again?
No, you just need to pass my map 2 arguments. You're passing it 1 argument. This is what so this is the thing about the types of procedures, right? They're very set in stone in a way. My map is a procedure that takes 2 arguments, right?
Yeah.
You're calling it with a single argument, so that's an error. It's just always an error to call my map with a single argument, because my map always takes 2 arguments. So what are the types of the arguments that my map takes?
Procedure and a list. Okay. Well, map takes a procedure and a list.
Well, so does my map. You're defining my map right here, right? And you can look at the argument list. The argument list of my map, is proc list. And that's really what we thought about right at the very beginning when I said, okay, let's think about what arguments this procedure is going to take and what it's going to return. It takes 2 arguments. And those arguments are a procedure and a list. And then what it does is it maps that procedure across the list. So this call to MyMap has to have two arguments, a procedure and a list, because calls to MyMap always have a procedure and a list.
So, I mean, is it just...
It's just proc. You just have to pass it proc back in.
But it needs a paren since it's a procedure.
No, because we're not applying it. So let's think very carefully about this. We use a paren to apply a procedure to arguments.
Okay.
Okay. But here we're not applying it, just like when you call MyMap with MySquare, for instance, we don't put parens around MySquare because we're in that call. We're not applying MySquare to anything. We're just treating it as a value. Procedures themselves are values in Scheme, just like numbers are values and lists are values. Procedures themselves are just values, and you can pass them around. So this is correct. If just make sure your parens are closed. They probably are. Yeah. So try running it and try applying it again.
That's better.
Okay. That's much better. So we've just done something really cool, right? Because, I mean, when we look at map, when we first just sort of look at it and you go, wow, that's really cool. That's sort of magic, right? It takes a list and a procedure and it returns to the list of them. But you can see, okay, we can actually implement that ourselves.
Yeah.
It's not quite as magic as we thought. It's something that we can do. So
this is recursive now. Wow. I have to we're still in recursion, huh? Because it's referring back to itself.
Right. We're still in recursion. And
So it goes through, the recursion is because it's got this list with multiple items and it goes through but I just it definitely is more intuitive with something like factorial, because factorial is kind of leading you to one. But this one, the value here is the list.
Right. And here's the thing. This kind of pattern of recursing on cooters is extremely common. And so we had some up there, which is sort of this intermediate step where we're still running down the items of the list using rest, but our combination is a little bit simpler, right? We're just adding, right? And we're returning numbers.
Yeah.
But when we write recursive functions that take lists and return new lists, it's very often this pattern. We cons something to the result of the recursive call made with the rest of the list as an argument, right? We can think about this again in terms of just sort of definitions, right? We have these two definitions. So what is the result of map on a list? Well, we have the base case. We say that the result of mapping a procedure across an empty list is the empty list itself. And the result of the definition of taking a list that has items in it, right? Could be 3 items, could be 4 items of my map with that. The definition of the result of mapping a procedure across a list that has a length greater than 0 is just the result of consing the first item, the result of consing the result of applying the procedure to the first item in the list to the result of mapping the procedure across the rest of the list, which is a little bit of a mouthful, right?
It's
it's a little hard to keep straight when you're saying it.
I mean, that's because of the mapping. The mapping thing is less, like, I don't know. It's more generalized than something like addition. Or,
It is. And that's something that's really nice about this is that, for instance, we don't have to, and this is something where, for instance, if you start looking at languages like Haskell that are statically typed, they actually do a lot of checking when you write the program at compile time to make sure that all of the types in your program line up. So in Haskell, if you are trying to map a procedure across a list and that procedure expects integers, the Haskell compiler is going to sort of check your code before it even runs and say, given the way that this code is written, is it guaranteed that the list is going to have things of the right type for the procedure? But note something really interesting here. It's not a concrete type. We don't know what that type is. We just know that the types have to match.
Yeah.
Right? The type of the items in the list has to be a type that procedure can accept. So if it's square, then we know that the list's type is going to have to be a list of numbers.
Yeah.
Right? We can talk about lists as having a type involving. Now, Scheme allows you to have lists that have different types of things in them, right? In Haskell, that's a little bit trickier. We don't really. We don't want to get into Haskell at the moment, but
okay, fair enough.
It's worth thinking about some of this type stuff, right? Because Haskell makes you be extremely explicit about your types. And
it's strongly typed. You were saying it's strongly typed.
Scheme is pretty strongly typed too. I mean, Haskell's actually even more strongly typed. But what it is that Haskell is statically typed. That is to say that you have to know what the types of things are before the code runs, basically. And you have to specify them. Haskell has something called type inference, where you don't have to specify all of your types. Haskell can kind of like, and other languages with type inference, can kind of take a look at your code and go, well, if that's of this type, and this is of this type, then this must be of this type. It has to be of this type. It can figure that out for you in some cases. Less sophisticated.
It's not.
I'm sorry?
Yeah. And then it'll tell you if it's not. That's the
It will tell you if it's not, and it will tell you right when you try to compile your code, right? Before you try to run it. And so there are some advantages and disadvantages to this. It's a little bit easier to just write quick code in dynamically typed languages sometimes, but you still have to bear the types in mind. The same sorts of type relationships that are explicit in Haskell are implicit in Scheme. And you get an error if you violate them, but you get an error at runtime typically in Scheme, whereas with Haskell you would get an error at compile time, right? But we still have this thing where these types still matter here. The type of procedure, we talked about how procedures themselves have a type.
Yeah.
The type of procedure has to include it taking as an argument the types of things that are in the list that you pass into Square. But note that this is not a concrete type. We know that it has to match, but we don't know what it is. So it is starting to get very abstract in a way, right? We're like, the procedure takes this type, it matches the type of the things in the list, but we don't know what that is at the moment, right? We won't know that till runtime, but they had better match or it will error. And that's something, this is a really, really interesting and deep topic. We're not going to go super deep into it in terms of talking about its implications, but everything that we do, we need to be thinking about these types. The types always have to match up. And that's why I've been kind of like hammering a little bit on the point of like procedures having a type. It's implicit. Scheme doesn't make you write it down or specify it, but you need to always be bearing it in mind. And the truth is that if you think about types carefully, it will kind of almost write a lot of your code for you, right? I mean, like it won't literally type it, but you just know what to type because you know what the types have to be. And it's just really clear. Okay, well, this kind of has to be this if these types are this. So it avoids a lot of confusion. It's an important tool for thinking about code and keeping yourself from getting confused about what's going on.
Cool.
So we also took a look at filter before. Do you remember filter?
Yeah, filter a list for a certain type of thing. Like we did like filter odd or something, and it returned us just the odd numbers in the list, something like that.
So why don't you try filtering a list for the odd numbers? Odd, by the way, is ODD question mark. It's a predicate, so it has a question mark on it.
And it's got, and then I need to do, oops.
Okay. So why don't we try writing my filter?
Right. Hmm. Okay, so let's see here. Filter is a procedure
It is.
that takes a list
It
and
takes two things. It takes two things.
oh, right, it's got odd. It takes a predicate. No, it's not a predicate.
It is a predicate, in fact.
Oh, it is? I thought predicate
Filter
was.
pretty much needs to take a predicate. A filter is a type of procedure that returns true or false.
Oh, okay, yeah, right. So it's going through those and saying if it's true, return it. True of the odd question, and if it's false, I don't know what it does with false, but if it doesn't return it, um, or doesn't add it to the list that it returns, or use it.
That's actually a pretty succinct statement of what my filter needs to do, in fact. Yeah, that's good.
Huh. Oh, okay. So the filter is a proceed. So do I do that same thing? Or do I do a procedure in a list?
Yep, that is the type. So what's the base case here?
Oh, why did it not indent it? Oh, because I did two prints.
Yeah, you have too many prints there. Yep.
So the base case, let's see, it's going to go through it until it comes to the end, but that wouldn't be an empty list, though. It would be, well, it might be an empty list, but it could.
Well, this is still going to be a recursion on cooters, right? So how are we going to, this is still going to be this thing where we are sort of doing something. It's still going to involve first and rest of the list, right?
Yeah. So I mean, I guess it would have to be.
Yeah, the empty list is still the pretty obvious base case here. And yep, indeed, that is the base case. The result of filtering an empty list by pretty much any predicate is going to be the empty list, right?
Okay. Yeah, it's going to go through
So
everything.
this bit gets a little bit tricky, and I expect that I will, probably have to give you a fair number of nudges here. Don't worry about that. This is a little bit tricky, but
Okay. Yeah, because it's not just a matter of kind of going through the list and applying. Well, I mean, I guess it is, but it's applying odd to each list.
well, we actually kind of have to have another conditional here, right?
Okay.
In the sense that we still have. So one of the things that's been true in every procedure that we've written so far is that, if there's things in the list, we always do the same thing. There's not a question about it, right?
Mm-hmm.
Like if we're doing factorial, we're always just multiplying this number by the next thing. If we're doing
Yes.
length,
Yeah.
we're just adding one. If we're doing sum, we're just adding a number. And if we're doing my map, then we're just adding a procedure. There's not a question about what we do, but there is a question about what we do here, isn't there?
Yeah, because we have to evaluate each item in the list before we decide what to do with it.
Well, we have to know what the predicate returned when given each item in the list, right?
Okay. Yeah.
Okay. So let's think about that. We have two cases now, right? We have the case where the predicate, returns true, and we have the case where the predicate returns false, right?
Yeah, I mean, I guess so. Doesn't actually give you a T or an F with the odd. It just either,
Right.
prints it at.
Sure, but we probably need to do different things depending on those two things, right?
Right, because we're trying to look under the hood, basically.
Right. We have to write filter now, so we have to know how. Right. The external behavior of filter and the internal behavior are separate things. The external behavior is just like what it does if I use it. The internal behavior is sort of like how do I actually make it do this?
Yeah.
And if I'm trying to make it do this, I probably do need to do different things based on the result of calling the predicate on the item, right?
Yeah. Okay.
So how do we make decisions here? How do we only have one real tool for conditionals at this point. So how do we do things based on the result of something? How do we do two different things based on the result of something? based on a condition.
It'll be two different things based on a condition. Uh, uh,
So how do we essentially express if this, then that, else this, right? 'Cause that's pretty much what we're doing here is we're saying, well, if the predicate returns true, do one thing, otherwise
Right.
do another thing, right?
oh yeah, how did we do that? I mean, I think it's if again, isn't
It's
it?
if
Yeah.
again. It's if again. I mean, I'm sorry. I mean, the thing about it is that it probably seems too obvious. You're looking for something that's not that obvious. So sometimes I will, kind of ask questions that have very obvious answers. So,
Uh, and the
sometimes
if
intentionally, sometimes unintentionally. But
and if has four parts. It's got the if. It's got the whatever that second thing is, and then it's better than the fourth thing. Sorry.
right, it's got the condition, right? So what's our
The second-
condition here? What's our condition here? What are we actually testing?
Well, true, false. I mean, odd, but we true or false. Whether the number is odd. Whether the
We're
thing-
interested in the result. We're interested in the result of applying the predicate to the
To
first
each
thing on the
item.
list, right?
First, yeah. Okay, so the condition is the result applying the predicate to the first thing in the list, and the predicate is whether it's odd or not.
If odd is what we happen to pass in, it's whatever proc is. Proc is the predicate, right?
Yeah, okay.
So we probably want to apply proc to the first item in the list, right? Right. Now we could write this out. Let's just note something here. We could write this out and say if proc first in the list equals true. If if it equals true, then do this, right? Else if false, do this. But we don't have to do that because if itself sort of takes a true or a false, right? So we can just say if proc first list, right? And indeed, if applying the procedure to the first thing in the list is true, then that condition will be true and the first branch of the if will be taken. Otherwise,
Yep.
the second branch will be taken. Do you see that? Does that
Yeah.
make sense? Okay.
Yep.
So let's make
and
sure.
so
I'm sorry.
that'll be the next two. But did I? Yeah, no, I closed up
I
the
think you
procedure.
got. Yeah. Can you just go one back and see like what it highlights? But I do believe yes. So that's the correct parens.
Yep.
I very rarely try to actually directly count parens. I want to look at what's being highlighted in the editor and how it's indenting things. Right.
Uh-huh.
If you hit return right now,
Oh, right.
because that's your condition. We have if condition. And most of the time for if, you do want to make
Yeah,
things
yeah.
multi-line, right? You put the true branch on one line and the false branch on the next line. So,
Well, but I haven't even done the true branch yet.
yeah. Well, that's what you're writing right now is the true branch, right? Like, if the procedure returns true, calling it on the first of the list, right? What do we want to return in that case?
We want to return the okay. So if the procedure returns true, then we want to return that first item. Don't we? Yeah. What's if? Okay. We want to keep it.
We want to keep it, but remember that when we're writing these branches of this if is going to be the last thing in the procedure, right? And so whatever that branch gets executed is going to be the return value of this entire invocation of the procedure. So this branch, we're now down to actually saying what the return value is. This procedure, what type is its return value? What type of thing does my filter return?
It will return the list.
Okay, so we know that this line has to evaluate to a list, right?
Right.
Because this if is going to be sort of the expression. This is whatever this if evaluates to. The whole call to my filter is going to evaluate to that thing. The if is going to evaluate to one or two, it's got two branches. Whichever branch is evaluated, the if itself is going to evaluate to whatever that branch evaluated to, right? So you can just sort of like go up from the bottom and say, okay, these all have to be lists, right? Either that or tortoises all the way down, one or the other, right? But like it's just lists all the way down. So so this has to we know that right off the bat, and that's kind of part of what I'm saying again about types. Types really guide you, right? They say, okay, so this has to be a list. So what is the list? What like, and sometimes even though we're writing this very abstract thing, where we don't know what the types involved are because we don't know what types proc expects, right? So we don't know what types of things are in the list either. It's got to match, but we don't know what they are. Just like with map. But sometimes it helps to think about a concrete example, like what if proc were odd and list were a list of numbers, right? So if proc were odd and we had a list that was, say, 2, 3, 4, right?
Yep.
Okay.
It's going to look at the...
In that case, that would be the next branch, right? So maybe that's not the best example.
What do you mean it would be the next branch?
So we're writing the true branch here, right? Which is if the first thing in the list is odd, this is the branch that gets executed. Well, I said 2, 3, 4 is the list, right? That's maybe not the example we want here because, in fact, odd would return false in that case. We want to maybe think about that when we write the next branch. But maybe now we want to think about, okay, what if the procedure is odd and the list is 3, 4, 5?
Yeah, I mean, it'll return 3. First on the list.
3? Well, okay. But let's think about that for a second here. What type of thing do we need to return?
A list.
Is 3 a list?
Yeah. Isn't it?
No, 3 is not a list. 3 is a number.
Well, I mean, but it'll return a list with three.
Okay,
as an item.
That's true. It will return a list with 3 as an item. But we need to define this in terms of some operation. So we need to define it probably in terms of a combination, right? The result of doing something to the first item in the list, which we kind of know we're not going to do anything to it, right? We know that 3 is going to pass into the result unchanged. So we can think of a trivial operation on something as just being something that doesn't change that value. In fact, there's a function in Scheme called identity, a procedure that does exactly that. You pass it something, you get the thing back, right? So we can think of that as being sort of the trivial case of an operation, okay? So we don't want to change 3. So it's sort of the operation. It's just, we don't have to write identity something. We just write the thing, right? That gives us back the thing. We need to combine that. We need this definition. We kind of know, because this is recursion on cooters, that we want to define this in terms of the result of calling my filter on the rest of the list, right?
Yeah.
Okay. So think about how you would write this line out then. If procedure return true, what do we want to return?
Well, a procedure. You mean which here? Because from the top level procedure, this one
No,
up here?
what I'm saying is the condition here, right?
This if, or?
No, the if that we're right inside now.
Okay.
Where we tested the predicate against this. So that's the thing. We are in this particular branch where the predicate passed. Okay. So what do we want this branch to look like? If we have 3, 4, 5 as our list and odd is our predicate, what are we going to return?
A list of 3. Because it's the first thing list. No.
If I ask you to filter the list 3, 4, 5 by odd, what do you get back?
List of 3, 5.
That's right. So it's not the list of just 3. It's the list of 3 and 5.
Okay, you're saying for the not the first thing here, but our. But what about first? We're trying to deal with just the first here. I thought, isn't that so?
Well, okay, this is the case.
Oh, but you're just talking about this part before you go inside these parens.
No, I'm talking about. So that if there is just testing to see, because we need to do two different things, depending on whether or not our predicate passes or not. right?
Yeah.
Because we could also have the case of like 2, 3, 4, 5, and we're going to do a different thing then, right?
Yeah.
Right? Which is we're going to drop the first item in the list. But if that predicate returned true, we're going to keep the first item in the list. But we still have to return the result, right? This is my filter. This procedure has to return the result of filtering the list by the predicate. So if we have 3, 4, 5, if we call my filter with 3, 4, 5, it has to actually return the correct result for that, which is 3, 5, a list containing 3 and 5.
Okay. But we have to have odd in here somewhere. It doesn't even know that yet.
Well, we already do. We applied proc to the first thing in the list.
Yeah.
Okay.
But how does it? We never told it that the proc is odd.
We don't. It doesn't need to know that. We just know that the predicate succeeded. We don't know that the predicate is odd. Whoever called my filter could call anything. They could have passed it, right? We don't know that at this point, but we do know that the predicate returned true when applied to the first item in the list. So if the predicate was odd and the list was 3, 4, 5, then this was true. If even were the predicate and it were the list 3, 4, 5, we'd be in the other branch. Do you see?
Yeah.
Okay. But we have to figure out what result we want for the entire function if the predicate returned true.
Well, it needs to be a list. That's about as far as
list.
With all the items that are.
Right. And how would you express that in terms of the first item in the list and the result of filtering the rest of the list? That's the key thing here, right? Let's look up above. In every case, I mean, we only had one non-base case branch in all of the other cases. This is weird and hard to think about a little bit because we have 2 potential branches for the case that's not the base case. But it's the same pattern pretty much, right? Which is that we need to express this in terms of combining the first item in the list, possibly modified in some way, with the result of making the recursive call on the rest of the list. Right? It's always that sort of definitional question. So
it's going to be one's the procedure, which is the
okay. What's the result of applying? What are you going to apply the procedure to?
I guess we already did it up there to the list.
Right. Does filter the result of filter, does it include the results of applying the predicate to the items?
Does it include the results of?
So if I pass filter odd in the list 3, 4, 5, right? I get back a list. Does that list include the result of applying procedure to any of the items?
Yeah, it does. I mean,
no, it doesn't. It just passes you the items. It either passes you the item back unchanged, or it doesn't give you the item at all inside the list, right? It does one or the other. So up there with map, we had to apply the procedure. We had to cons the result of applying the procedure to the first thing in it because the result itself includes that result, right? If we pass it my square and 2, 4, 6, the first thing is going to be a 4 and the second thing is going to be a 16. So our result has to include the result of applying the procedure to the items of the list. Okay. But when we do odd 3, 4, 5, what's the result of applying odd to 3?
True.
Does the result that we get back, does it contain a true within it?
No, it just contains
the items themselves.
List. Yeah. Okay. So
the whole purpose of the procedure, of passing in a procedure odd, is to tell us which branch we're taking here. That's all. We don't have to use the procedure ever again. The whole point of it is to be in that if statement.
Okay, so that I'm just going to, if it's, it cons that to the remainder of the list, that's also, I don't know, maybe not. Maybe it's just the remainder of the list because it's going to go through each item and do that again.
Okay. So I'm a little bit unsure of what you're saying, but why don't you type something and it'll become clearer what you're thinking.
Right. Oh no, I can't do the. How do you do fonts? Do the. Oh, here. Procedure left.
Okay. So that seems pretty reasonable. That's an attempt, and we'll see how successful it is. That's an attempt. I mean, I would say that either way, regardless of how successful it's going to be. So don't think that that means that it's wrong or right. We'll find out. What about the false case?
Yeah.
What about the case where the list is 2, 3, 4, and the predicate is odd?
And then if the. So I need another if here.
You don't need another if, right? If has 2 branches already, right?
Yeah, right. If has 2 branches, though. Okay.
So, but we just need to write the second branch, the branch that corresponds to the predicate returning false.
Yeah. I don't know. It's... Huh. Well, you're still doing the procedure.
Well, hang on.
What?
We didn't apply the procedure to anything in the first branch, did we? We passed it into the recursive call because you just have to keep passing the procedure down recursively, right?
Mm-hmm.
But really, the whole purpose of the procedure in this is to be in that if statement. We're done with the procedure at this point. The entire point of the procedure, right? We never have to incorporate the results. That's what I was saying before.
Yeah.
You don't have to incorporate the result of calling the procedure, of applying the procedure to the items of the list. You don't have to incorporate that in the result, right?
Mm-hmm.
When you have 3, 4, 5, 6, and you pass that in with odd, in what you get back is 3 and 5. You don't see, that true false is not incorporated in the result, but it's necessary to make the decision as to whether or not to include things.
You only just have to call it once.
You just have to call it once, because really what these 2 cases are about is the first one is yes, I want to include this in the list. And the second case is I don't want to include this item in the list, right? That's what these branches are doing.
So it's the first of the list again.
Well, let me ask you something. What does this branch have to return? What is the type of thing that this branch has to return?
An empty, well, no, not an, has to return the null value or something. I mean, has to return nothing.
This is the result of calling my filter. Okay, this is okay.
Oh, you're saying the whole thing or
this branch? This branch. So let's go back to this thing about it being lists all the way down, because this is a really, really important point, and it's one that can be very hard to see at first.
Mm-hmm.
My filter is a procedure, right? It's going to return something.
Yep.
What type of thing is my filter going to return?
A list.
A list. Okay. So my filter has a single expression inside it, okay? Which is that enclosing if.
Mm-hmm.
Right? So my filter, the very first if.
Yeah.
My filter has to return a list, which means that if has to evaluate to a list, okay? Mm-hmm. Now an if has 2 branches.
Yep.
One branch or the other will be evaluated, and the entire if will, what it evaluates to will be whatever the branch that gets executed, that gets evaluated, evaluates to, right? Is that clear? Okay.
Yeah.
So we can look at that first branch of that if up there, and we can say, okay, that evaluates to a list. It happens to evaluate to the empty list. It's always going to be that, right?
Mm-hmm.
Okay. Let's look at the second branch of that if. What is the second branch of that first if?
The second branch of the first if is, is this part that we've started down here.
Well, it's another if. It's one expression again, right? It's one expression because, leaving aside some cases that I want to talk about, the branches of an if are just one expression, okay? Each branch is just a single expression, and it evaluates to a single value. So that whole first if has one branch that we know evaluates to a list. We know that first if has to itself evaluate to a list, which means that both of its branches have to evaluate to lists, which means that this inner if also has to evaluate to a list. Do you see what I'm saying?
Yep.
Okay.
Sure.
So an if has two branches, and each of those branches, one of them will be evaluated, and the entire if will evaluate to whatever that branch evaluated to, whichever one it is. So we know that both branches of this inner if, they both have to evaluate to lists, because this second branch is going to be taken, and it's going to be the entire return value of my filter, right? If we happen to hit this branch and it's the one that's evaluated, this branch of this if is going to actually be your result. So we can think about the case where we pass my filter odd 2, 3, 4, 5, because that's the case that we're talking about. What does my filter evaluate to in that case?
A list containing 3.
Okay. Did I just say 2, 3, 4? Let's say 2, 3, 4, 5.
Oh, yeah, you did say 5. Sorry, a list containing 3, 5.
3 and 5. That's the result of my filter in that case, right?
Yep.
If we hit this branch, note that this branch will be the return value of my filter. Do you see that?
When you say this branch, which
the
one
branch
do you
we're
mean?
writing right now.
Uh-huh.
If we hit this branch, if this is the branch that we get to, which it would be in that case, right?
Yeah.
Because we'd say, okay, it's not the empty list, so we're going to take the second branch of that first if. Okay.
Yeah.
Then we're going to get to this if, and we're going to say, does the predicate return true on the first item of the list? And the first item is 2, and the predicate is odd. So we're going to say, oh, okay, no, it doesn't. So we're going to evaluate the second branch of this if that we're in. And what it evaluates to is what the entire call to my filter is going to evaluate to.
Yeah.
Okay.
Sure.
So what does this branch have to evaluate to in that case? If the predicate is odd and list is 2, 3, 4, 5, what does this branch have to evaluate to?
It has to evaluate to a list that
And what
returns
list?
3, 5.
Well, a list containing 3 and 5.
Yeah.
Right.
What did I say?
A list
that contains 3, 5.
that contains
Yeah.
3, 5. The list 3, 5. So this branch has to evaluate to the total result of my filter in that case, right? Each of these branches does. You'll note that there are 3 terminal branches of these ifs. There's the one that's the empty list, right?
Yep.
There's the one we just wrote,
Yep.
and there's the one we're writing now. Every single one of them is going to be the return value of my filter under some set of circumstances. Okay. So that's the point here. And when you know that, then that just makes everything very clear.
I mean, would it just be the same thing again? But that doesn't.
Well, what do you mean by the same thing again?
The same, the exact same. If it's this. I mean, it seems like we need another. Oh no, we don't need another if.
No. But we need to be able to express our result in terms of the first of the list, the first thing in the list, and the result of making a recursive call to my filter with the rest of the list. Okay.
Okay. Right. So in this case, we don't want a cons. If the
That's right. So, and I'm going to really break this down again, because this is how you think about these kinds of things, which is that you think about expressing them in terms of possibly doing something, in terms of the first thing in the list and the result of the recursive call to the rest of the list. Okay. So we need to define it in terms of that. So let's say that our predicate is odd.
Yep.
And our list is 2, 3, 4, 5. What is the definition of the result that you want? What is the result you want expressed in terms of 2 and the result of filtering the rest of the list?
You want to, I mean, that's not the proper, I mean, you want to throw out the two
Okay.
and then evaluate the rest of the list and throw out any
Well,
other non-odd numbers.
Exactly. And that's actually exactly what you want to do here.
How do we throw something out though?
You just don't cons it.
Yeah.
Cons is why we included it in the first thing. So I'm just going to like cut to the chase here a little bit, and I think it'll become very clear. I wanted to go through it at least this much though to get you to this point, but I think at this point, I think that like a light will dawn now when you do this.
Yeah.
Literally just make the recursive call. The result here in terms of like, so we assume that my filter does the right thing, right? That's part of how we think about recursion. We just say, okay, my filter is going to properly filter the rest of the list if we do it. Well, so if we have 2, 3, 4, 5 and it's odd, what do we want? We want the rest of the list filtered for odd. That's it. Okay.
So you're saying it's just...
It's just literally the recursive call.
That's the whole thing.
You have to close up some parens.
Yeah, that's, I mean...
Yeah. So why don't you give it a try? You may want to pull that up just a little bit. Make that just a little bigger. Yeah, there we go.
So we've got my filter and one list.
Well, what's the first argument that my filter takes?
All right. We need to decide. So, but we should be able to do it with either.
Yes.
So it is.
Yeah. Any predicate that matches, that accepts things of the type that are in the list, that the items of the list belong to.
And then I guess it shouldn't really matter. Let me give them a couple. And it doesn't have to, the list doesn't have to go in order though either, does it?
No. Order does not matter here.
Interesting.
Hey, so it worked. Right.
I don't know how I knew that.
How you knew what?
I don't know. I can kind of follow along, but I gotta say it's not totally. I would be hard pressed to I have a hard time thinking all the way down through it. I guess it's kind of
listen, this is tricky. This tends to. You're actually. I'll say this. You're picking this up faster than most people do.
Yeah, I appreciate that.
Like recursion, actually, you still have some trouble with the basic mechanics of Scheme. I think it would be really helpful for you if you can find some time during the week to just write some very simple code, right? Just simple stuff like something to like calculate the volume of a sphere, right? Given the radius of a sphere, right? Just write that as a function. Just say that's something I want to do. Just like really, really simple sort of exercises like that, just to get a little bit better with like this feel for like, okay, I use an open paren to apply a procedure to things, right? And then the rest of the things inside before the close paren are the arguments to that, right? Because you're actually struggling more with that than with the recursion. But it's hard when you don't have those basic mechanics at your fingertips.
You kind of get locked up by that to think about the actual process.
It's like I've been playing some piano lately, and it's this thing where there's like hand independence, right? Like you have these two different hands, and they're doing different things rhythmically, and that's kind of hard, right? So one of the things about it is you can't think about the musicality of what you're doing, right? Making it sort of sing and be nice and musical. You can't even think about that until you have the thing where your hands are together, and that's pretty automatic, right? Well, together when they have to be together and not together, because of course I'm a guitarist at heart, and I spent years synchronizing my hands because that's the challenge in guitar, right? Is to get your hands doing the same thing at the same time. And in piano, the challenge is a little bit different because you want your hands, yeah, doing the same thing at the same time some of the time, but then you sometimes want them doing completely different things at the same time. And that really, it's tricky. But here's the thing. When you're struggling with the mechanics of like, can I get my, you can't think about dynamics easily. You
Yeah.
can't say, oh, I want this to be, nice and soft and this to be loud. And I want to like have a little bit of nice rubato here, right? So, but it's the same thing. When you're struggling with the mechanics of it, it makes it harder to concentrate on the big picture. So I think you would benefit from working on the mechanics a little bit. However, like you're doing fine. This one's hard, and for some reason, this filter one, I have kind of showed recursion to people with kind of similar sequences of stuff before, and this one tends to trip people up, right? Like, it is tricky. The thing that I was trying to emphasize there is, tell you what, I need to use the bathroom, and I want to grab a refreshing beverage as well.
Yeah.
Let's take like just a break for just a couple of minutes, and we'll come back and we'll talk a little bit about this procedure. Does
Cool.
that sound good?
Sounds
Okay.
good.
I'll just be back in a minute then. Okay.
Great.
Okay, I am back. It sounds like you're there as well.
Yeah.
Yeah. Okay.
Chat out.
So, let's talk a little bit about this. Like, I think I want to really emphasize here this thing that I was saying before, but I want you to really take a very close look at this, right?
Yeah.
This is something where when you've been writing this kind of code for a while, this is just super, super obvious. You just look at it and you see what it does. But it's not obvious when you start writing this kind of code.
Yeah.
Which is this thing I've been saying about what the whole thing evaluates to, right? Like my filter evaluates to, applying my filter to something, right? It's going to return, which means that call is going to evaluate to whatever that if evaluates to, that first if, right? Because that's the whole body of my filter. The whole body of my filter is one expression, right? And that expression is that if. So whatever that if evaluates to, that's what my filter evaluates to. Right? So that if is going to evaluate to whatever, which, one of its branches is going to be taken and the other one's not going to be taken, right? So whichever branch gets taken, it's going to evaluate to whatever that branch evaluates to. And so that's really clear in the first case, right? It's the empty list, just always the empty list. In the second case, it's a little less clear, but note that that's an if. It's also just one expression, right? So if that second branch gets taken, that outer if is going to evaluate to whatever that inner if evaluates to, right? That's what that whole outer if will evaluate to, meaning that's what my filter is going to evaluate to.
Yep.
And again, it's the same thing. That inner if is going to it's going to evaluate one of those two branches. That inner if will evaluate to whatever the branch that it takes evaluates to. And that's what the outer if is going to evaluate to, meaning that's what the entire application of the procedure does. I think it's just really important to keep that in mind. And I think that if you sort of keep that in mind, it makes thinking about this a lot easier, right?
Yeah, I mean, I think it's further down I can kind of get that on a little bit above a larger scale. Like there's these chunks of things like if, okay, not an empty list, then proceed to the second branch here. And then if, okay. And then it gets a little bit murky for me here.
Well, so here's the key insight, which is that each of these branches in that inner if, it's the entire work. Like its result is the result of the entire procedures. Because one of the things you were sort of starting to think while we were writing it is, oh, this should just be sort of the 3 or something. This should just return the 3, this line. But it can't just return the 3. It has to return a list because the entire my filter function is going to evaluate to whatever this one single line evaluates to. So this line has to evaluate to the result. This line by itself. You see what I'm saying?
Yeah, this line meaning whichever the
I mean, the branches of that inner if are individual lines of code, right? Each branch is on its own line. So when those get hit, the entire call to my filter is going to evaluate to whatever that line of code evaluates to, either line 39 or line 40, right? Do you see that?
Yeah.
Yep. So that's the critical thing is that you're sort of still thinking as if like, oh, this is only part of the work of this, right? I mean, in a sense, it's only part of the work because the recursive call is, that you're making is going to be doing quite a bit of the work, but that recursive call is on this line. This line has to include that. This line has to encompass all the work that we need to do for the entire function. The entire function call. And that makes it, I think, a little bit clearer.
Yeah. I mean, I think I'm maybe just there's like I think there's I mean, I understand. I feel like I'm kind of getting the basic of the recursive process, or but there's almost like a visualization that I'm trying to do that I can't quite get to, which is maybe unreasonable.
I mean, it's pretty reasonable to find this a little bit. I mean, like I said, people tend to struggle with this. This tends to be hard. I have watched, people. I mean, when I went to university, which was a long time ago, but recursion was briefly introduced at the end of the first semester, and then Generally speaking, a course that most people took the second semester. Actually, that's not even true. It was the end of the second semester for most people. I just didn't take the first course. So people were already basically about a year into the computer science program before they even really saw recursion. And it really didn't get picked up until, generally speaking, a course that people took the first semester of sophomore year, right? Now, part of the reason for that is that historically recursion was seen as a little bit exotic for kind of historical reasons. It's really not as hard as people have made it out to be in many respects, and it is much more fundamental than people have. And there's just historical reasons for this. You'll note, for instance, that SICP, which is a freshman textbook at MIT, right? SICP introduces recursion right off the bat, just like we're doing, because it is really fundamental. But people do have a hard time with it. And I watched people who were like a year into a computer science program really, really struggle with recursion for a while, to the point where it was one of the things that made some people drop out of the major, right? The department that I went to wanted to remain small, even though it was part of a large public university, at a time when there was a lot of interest in programming, right? So one of the things that they did is quite intentionally washed the majority of the people who wanted to be comp sci majors out of the program. I would say there's a survival rate of about a third of people who wanted to be comp sci majors and wound up being comp sci majors, which you could discuss whether or not that's a good thing or not, but it was their approach to things. So there were a few things that tended to knock people out of that program, and one of them was certainly pointers. C. This is some stuff that doesn't directly come up in Scheme. You don't manage them directly. There are still plenty of pointers. People have a hard time with pointers. And recursion was another one of them. And then there was this one guy we had who was this really famously curmudgeonly instructor who also washed a lot of people out just because he was so hard to deal with, actually. And I avoided him completely by taking the course that he taught over the summer when it was taught by a grad student, which was probably one of the smartest things I ever did, because that course was not enjoyable from everything I've heard about it. So anyway, so just, be aware. People have a hard time with recursion, and it's the kind of thing that becomes really, really obvious once you've done it a lot.
I can see that.
But maybe we should just do some more of it in that case. I would like to say, though, if you're looking at my filter and if there's some stuff about it that's vague, that you're having a hard time, that's kind of slipping, a little slippery for you still, maybe we should look at that and try to unslipify it, if that makes any sense. Try to nail it a little.
I think I'm getting the kind of what did you call it, the recursive phrase or whatever, that process there, or that
recursion on cutters.
Yeah,
right.
That makes sense. I'm not being able to visualize how. Okay, and I guess the parens kind of tells it that. Now let me look at the parens here. So this was that one. That goes that one to that, and then so this is all if. We take this procedure to the first of the list, and then this is the second. Well, it's not a second branch. This is still part of the first branch of this inner if, right? This is all the first branch.
That is the first branch of the inner if. Yeah.
Okay. All right. Because this is the if has to be applied to the procedure in the list. So this is the procedure, there's the list. Right. So here's
that's the condition of the if, right? That's the truth value. So this branch gets executed if the predicate returns true when applied to the first thing in the list. So basically it's like if it's odd in 3, 4, 5, this branch is the entire return value of my filter, right? Because you're like, okay, yes, if odd, first thing in the list, which it is, 3 is odd, then return my first branch, return line 39, right?
Sure. Of course, we asked it for even when we called my filter, but
we have to what? I'm sorry.
We asked it for even. When we called
right? Right. We could either way. If it's even, then
right?
Sure.
But it's kind of.
So let's think about what actually happens here. Let's go back. And like I said, the way we've been thinking about this, that there's a couple of different ways of thinking about recursion. And one of them is to think about it in terms of definitions. And that's really the right way to think about it most of the time. The other way to think about it is what the actual procedure calls are doing, right? What's actually happening, how many times the procedure, this procedure gets called and what it gets called with. So we could think about that because it can sometimes help to think about that while you're trying to understand recursion, because it does seem a little magic at a certain point. Like, how are we even getting a result here? Where is this result coming from? Right?
Yeah. Like I said, I mean, I can just like walk through factorial, and that's just, I'm like, oh yeah, totally. That makes sense to me. And I don't know why, it's different. And even the recur length, that made sense. You just, adding, you're taking the rest of the list, adding it, and then you're kind of going down through until you've, applied it to every item on the list. Well, and not in the case of length, but
Well, you have.
What?
I guess you are. You're applying. What you can think about it is this. You can think about it. Let's say that you had a function that no matter what you gave it, it returned 1. Mm-hmm. You could call it like count, right? Like every individual item you give to count, it returns 1 for, right?
Mm-hmm.
So you can think about recur length as being something where you are combining the result of applying count to the first thing in the list to the result of the recursive call on the rest of the list. Do you see what I'm saying?
Yeah.
It's just that that's a trivial sort of thing. You don't actually need to have count that always returns 1 because you can just write 1, right?
Yeah, sure.
But it's still the same shape of things. It's just that in this case, it's sort of trivial. And that's actually true of our last branch, line 40, which is that it's sort of the result of combining, right? You can think about it as kind of like, this is just sort of a very trivial combination of like not adding something to a list, right? Like that's a kind of combining things. That's a way of combining things. One way of combining the first item of the list with the recursive call to the rest of the list. One way of combining something with a list is to throw it away and just return the list, right?
How does it?
That's a trivial kind of combination.
How does it even know we're doing a predicate here? I guess is kind of what it comes down to.
Well, it doesn't. What happens is you apply odd to the first thing in the list, or even. Okay, you apply even to the first thing in the list. So
I have to know how to apply my filter. Yeah, of course.
Well,
like I can't say my filter, whatever.
You have to pass it a predicate. Note though that a lot of things in Scheme are kind of predicates because this is something that it's the whole truthy falsy dichotomy, right? I'd rather kind of look at this as just like that procedure is something that has to return true or false.
Yeah.
But do you remember when we talked a little bit about truthiness and falsiness?
Yeah, that basically it views anything that's not false as truth.
That's true. Pretty much, yeah, pretty much. So most procedures, let me put it this way. If a procedure can return false, it's pretty much a predicate, right? Because it either returns something truthy or it returns false. And I suppose trivially you could have a predicate that just always returned true. And in that sense, any predicate with a return value, any procedure with a return value could in a sense be thought of as a predicate, right? That's really weird though. We really want to think of predicates as being things that return true and false, right? Mm-hmm. Well, the whole point to if is if looks at the truth value of things to make a decision as to which branch to evaluate. That's the whole point of if, right?
Yeah.
Is we're like, we want to do different things depending on the truth value of something, right? We're like, if this is true, do this, but if it's false, do this. And really that's if it's truthy, do this, but if it's false, do this, right?
Mm-hmm. And in the form of if, it just has that built in. We've got the two branches laid out there.
Yeah.
And so it knows to go with the true one first and the false one.
Yeah. And one thing that would make this a little bit simpler, actually, and that might make this a little simpler to think about, is there's another conditional in Scheme called cond. And cond isn't just like an if this, then this. Cond is more like if this, then this, else if this, then this, else if this, then this, else, if none of those things were true, return this. That's kind of, do you see what I'm saying there with Kant? That's, that might not have been super clear. It's clearer on the page. So one thing that I have been thinking that we might want to do a little bit is actually take a look at SICP, because we're getting to a point where we've covered enough groundwork that we can look at some SICP and it will start to make sense. Maybe pop SICP up right now, because they write, I could, I don't know if I can control your screen, and I think if I could, it would be really laggy. I really kind of want to show you something without talking. I want to show you something visually, but I don't have a good way of doing that, but I know that it's in SICP.
Okay.
And in fact, actually, Cond is a good thing to know, and it might be reasonable for us to rewrite my filter to use Cond, and I think it might actually make my filter a little bit easier to think about. So yeah, unfortunately, we're going to suffer terrible, terrible lag here.
Okay. Well, let's try this. That'll help some, probably. SICP book.
Yeah, SICP by itself will pretty much probably turn the book up. I'm still kind of sitting here waiting.
Yeah, it was kind of okay. We'll just go to where we were at before. I'm loading up the MIT PDF of it right now.
The PDF? Okay. There's an HTML version, which is actually quite possibly what you want, but
this is what we were using before.
Too. Okay, this will work too. There is an HTML version. So if you jump down into building abstractions with procedures, right? That's sort of the very first section of the book. You're going to want to scroll down a little bit, right? This is stuff we've talked about. As I said, I would really strongly suggest going and reading SICP up to maybe about section 1.16 at least. They go back over a lot of stuff that we've gone back over, that we've gone over, and they come at it from a different approach, and it's a great book, right? And it's pretty simple it's pretty simple until you hit 1.16. It gets a little more complicated then. It starts talking about recursion. But going over some of this might help you with some of the basic mechanics too. Just seeing it from a different perspective, right?
Cool. We're down to recursion.
They're not really talking about recursion a whole bunch here, but yet. So, here we go. Cond. Okay. So this is Cond. Cond is a different kind of conditional, right? We use if to say, okay, if this thing is true, then this first branch, else this second branch. They actually introduced Cond before if in SICP, and Cond is a little bit harder to deal with, partially just on a purely mechanical level of parentheses, right? The syntax of Cond is a little bit more complicated. Now, again, just like if, we know that Cond is a special form. And we know this partially because that syntax would be illegal scheme if it weren't inside a special form, right?
Yeah.
But we also know that because Cond controls the evaluation of its arguments. So you remember we talked about this thing about how an if, it has two branches, but only one of the branches gets evaluated?
Yeah.
Okay.
How does it? What if it looks at doesn't it have to? What if it looks at one of them and it's not? Yeah, I'm trying to remember how that goes.
Well, okay, you have an if, and we have a test expression, and then you have branch 1 and branch 2. So the if looks at the test expression, and if the test expression is truthy, it evaluates branch 1. Otherwise, it evaluates branch 2, right? If we tried, we could write a function that was like if, that worked under most circumstances. But we couldn't quite write if as a function, as a procedure, because if you pass two things to a procedure, right? If you have something that's the shape of an if, but it's a procedure, it would evaluate both branches before even calling the procedure, right?
Yeah.
And we don't want both branches to be evaluated. And so the same thing is true of Cond, right? Cond, we noticed that about or and and as well. Or and and both will stop evaluating things when they get to the thing.
Yeah.
Right. If it's or, if you hit any true value, you're done. You don't have to evaluate anything more, right? So or just stops there. So you know that or is a special form because of that. The same thing is true of and. As soon as it says...
I have a question because I was looking back over one of the other sessions, and there was XOR. I couldn't remember what that was. Is that it?
That's like the super salad conditional, right? So if you're in a restaurant and they say, super salad, and you're like, yes,
Yeah.
that doesn't fly. Soup or salad does not mean that you get both soup and salad. That's not, right? So our or is, though, right? If you give or two true values, it will return true. Exclusive or means one of these is true and the other is false. That's what it's testing for. So if you give exclusive or two true values, it returns false. If you give it two false values, it returns false. But if you give it true false or false true, it returns true.
Or you can give it multiple, more than two values, or is exclusive?
So how does that work in Scheme? Because obviously with or and you can. I'm going to say that if you give it more than one value, I think it's just one of them is true and the others all have to be false. But maybe not. Maybe it's... Hang on a second. Let me actually try it out here.
Sorry to say. Maybe it doesn't.
Okay, nope. Exclusive or just you give it two things. It can only accept two things.
Okay. Cool.
So
and then so with cond, is it all? It's question is.
So you can look at what they're defining here, which is a function to calculate the absolute value of x, right? So this is just sort of a definition of this. Let's think about what this does, and then we'll look at the syntax more closely, right? So it says, if x is greater than 0, return x, right?
Yep.
If x is equal to 0, return 0. And if x is less than 0, return negative x. And applying subtraction to a number, to an integer by itself gives you, or to a number by itself just gives you the negative of the number, right? That's just part of how subtraction, basically that subtraction procedure works in Scheme. So knowing that's what this does, we can kind of look at the syntax and figure out how it works. So cond takes a number of forms, right? Note that these things are not, well, actually, no. Cond actually, it takes it takes a number of forms. These are all their own forms. Note that this isn't all bundled up into one big list, right?
Yeah.
Okay. So that's to say it opens some parens on that line and then it closes them. Each one of these lines is its own form, right?
Got it.
I mean, actually, whether it's technically a form, whatever. But I'm just going to be a little sloppy with my terminology here. So each of these things that it takes, so you have an open paren, you have something that is going to evaluate to something truthy or falsy, which is pretty much anything, right? But usually it's going to be something that evaluates to true or false, right? Kind of. We'll talk about that in terms of or and in a minute, right? About how the truthiness really matters there. But okay, is x greater than 0? No, right? So, it depends on what we pass it, but let's say that we pass this 3, okay? We pass abs 3. So it just kind of looks at that first line. It evaluates greater than x0. And indeed, x is greater than 0 in that case. So it returns the second thing in these parens, right? Which is x. So the first thing is a test. And the second thing is what to evaluate to. What we want the cond to evaluate to if this test passes.
Yep.
And if this test passes, the whole cond just evaluates to that second thing there, and we're done. And it doesn't evaluate anything further down. However, if that conditional is false, if it is not truthy, which pretty much means false, then we go on to the next one, and we say, okay, so let's say that we passed -3 to abs, right? So it would look at that first thing. It would say, okay, is x greater than 0? And indeed, it is not, right? So we go down to the next thing. We would say, is x equal to 0? And -3 is not equal to 0. So again, we don't know how to evaluate this cond yet. We haven't hit the clause that it evaluates to. And we get down to this last clause, and is x less than 0? And indeed, x is less than 0. -3 is less than 0. And so we say, okay, we want to return negative x. Well, -3 is 3, right?
Yeah, sure.
If we negate -3, we get 3. Because this is a function to calculate the absolute value of a number, right? What's the absolute value of -3?
I've forgotten that, but yeah, it's 3, huh?
It's 3,
Absolute.
right? That's what this procedure does. Right, it's named abs. Boom. So
Absolute value, okay.
yeah.
So then why is the negative x on the third line there have its own parens?
Because we're actually negating it. They're using so you
Okay, because negative, right? Yeah. You're performing a function on it.
You are, and that so the minus sign in scheme, right? It performs subtraction.
Mm-hmm.
If you apply it to a single number, it subtracts that number from 0.
Mm-hmm. Okay.
Right. Do you remember how plus works that way? If you apply plus to a single number, right?
Yep.
The lag is so bad, I don't really want you to switch back over to the other thing.
Yeah.
But if you apply plus 2, 3, you get 3 back. What it's basically doing is adding 3 to 0.
Yep.
If you apply negative to 3, you get -3 back, because what it's doing is subtracting 3 from 0.
Mm-hmm.
Now,
Okay.
if you give it -3, right, you are subtracting -3 from 0, and I know it's a little bit wonky, but if you subtract -3 from 0, you you get 3.
Yeah.
You get 3.
Because
You can think of subtraction as being addition, right? Subtraction's actually kind of a made-up thing, right? There is no subtraction. There's just addition, right? Subtracting is just adding the negative of a number to something.
Yeah.
Right?
Yeah.
I don't know. Depends on-
And then it's so where is this? It's close. It's going all the way. Yeah. Okay, I got it. Right. Yeah, this is then those last parens close all the way up to the define because it wanted to. You didn't necessarily have to have the define here, but it'll use it for later.
Well, if you want to have something named abs that takes a
Yeah.
number and does this, then you do need the define, right? That's why it's there, is to give this
Yeah.
type of thing a name, so that you can apply it to all kinds of numbers without having to write this out longhand every time, right? That's why we define procedures.
Sure.
And you can see that they're giving you a little bit of this kind of template-y syntax is very common in programming documentation, where they have placeholders in here, right? And they're saying, do you see the P1 and the E1?
Yeah.
Okay,
Yeah.
and note that those aren't parens, right? Note that those are pointy brackets,
Yeah.
right? So that's just telling you this is an entity P1 and an entity E1. We don't know what these things are, right? But yes, the first expression in each pair is a predicate. There we go. We're talking about it, right? So P1 is a predicate, an expression whose value is interpreted as either true or false. Note that they're also being sort of careful. They don't want to say that does evaluate to true or false, because is interpreted as true or false, right? That's that truthy-falsy distinction there.
Mm.
And so they're explaining it here. Conditional expressions, you can scroll down a little if you want, right? Get a little more on the page. But the predicate P1 is evaluated first, right? If its value is false, then P2 is evaluated. If P2's value is also false, then P3 is evaluated. That goes on until they find a value that returns true, in which case the interpreter returns the value of the corresponding consequent expression. Those E's are consequent expressions of the clause as the value is. They're quite precise with their terminology. So,
And none of them. Yeah.
now, note that as long as what you are passing to abs is a number, and it had better be, because things are going to blow up if they aren't, because you're using operations that expect numbers, right? Like greater than expects a number.
Right.
So
And is that a type thing again? That's
that's
you
a
just
type.
call it
The type of abs. The type of abs is that it takes a number and it returns a number. That's the type of that function. And again, these are implicit types, and you can pass it the wrong thing and it will blow up at runtime. If we were programming in Haskell, it wouldn't work that way. Haskell would refuse to actually compile your program unless Haskell itself could prove that everything you were passing to it was a number, right?
Mm-hmm.
But we won't, yeah. For us, that's implicit. You just have to get your types right. If you don't get your types right, things blow up.
So when it says in the last line of that paragraph or sentence, none of the p's is found to be true, the value of the cond is undefined. How would it print that? Like, how would it express that? Did I lose you? What happened?
Oh, I'm sorry. I was muted briefly. And I did not realize that and did not unmute. So, it would be, I think, the absence of a value. You know how we've hang on 1 second here. So go. Yeah. So you can actually try it out. I'm just gonna paste you something, right? That's just sort of very simple code you can pop into Racket. Right? You just pop that into Racket, and unfortunately lag. This is gonna but I'd like you to sort of see this, right?
On the false. So it's saying it's condition.
So what that's doing is it's got one expression to test, and we're just saying false, right?
Mm-hmm.
We're just flat out literally giving it. So what it's going to do is it's going to go and it's going to look at it. It's going to say, okay, is this true? If it is, I'm going to return 3. But false is not true. It is not even truthy, right? So it's not going to return the 3. It's not going to evaluate to the 3. It's going to say, oh, I ran out of cases. So, and we've kind of seen this before. What does print line return, right?
It returns the string that you.
No, it does not. It prints the string, but it does not evaluate to the string. So if you type in print line here and give it a string, right? Do you see how that's printed in a different color?
Yeah, sure.
That's telling you that that's something that got printed. That's not what printline evaluated to. Printline printed that. And that's a different thing. That's a side effect. But printline actually evaluated to the absence of a value. And if you type in open parens values, close parens, right, values when past nothing also returns. It evaluates to the absence of a value, basically. Okay. Note that is different than a value that indicates nothing. We've talked about that a little bit before too. That there is a distinction between having a value that is nothing, which in Scheme is pretty much the empty list, which you can also write null if you type in null right now.
Yeah.
Well, not in parens. You're not applying it. Remember, the parens are for applying procedures, right? We're just evaluating the value null. And you get the empty list. Null and the empty list are synonyms. That is a value. The empty list is a value. It is not the absence of a value, but it is a value that represents nothing.
Mm-hmm.
Right?
So values, what is values to? Is it, I mean, if
values, well, try typing in values 3. That gives you 3. Try typing in values 3, 5. Values allows you to basically, I don't want to get too deeply into this, but it allows you to, for instance, like a procedure has to return a single value in Scheme, right? Well, it doesn't have to, but it normally does, right? Like when you write a procedure out, there's a single value. What if you want a procedure that actually returns more than one value? You can do that by having a call to values in it. It basically evaluates to more than one value. Note that this is different than evaluating to a compound value. Like you can make a list out of 3 of 5, right?
Yeah.
But that's a single value. It's the list containing 3 and 5.
Yep.
What you're getting
Okay.
back from values here is actually 2 separate values. Right? So
Cool.
there is the absence of a value, and that's pretty much, and they're calling it undefined over there. That's pretty much, I just want to make that distinction that there is a difference between the absence of a value and a value that indicates nothing, right?
Yep. Yep.
A value that indicates nothing is still a value. And that is what null and the empty list are. So sorry to belabor the point and repeat myself, but it's an important.
No, it's okay. It's good. Good. What do you call that? Refresher.
Okay, so let's jump back into SICP though. We've got about half an hour left, so I think we could quite profitably probably spend the next half an hour just kind of looking at some stuff in SICP.
Cool.
Although, there was another idea for another recursive function that I thought might be interesting to write, but I think they actually get into some interesting stuff, which I think we're now at a point. It's too difficult, I think. I wouldn't want to use their first example of recursion as my first example of recursion with you, because there's too much extraneous stuff that can confuse, just is confusing. So, like I said, SICP is kind of a hard book if you're not already a programmer. But, so let's note something about ABS, though. ABS is exhaustive in its cases, right? That is to say that, assuming that your types are correct, that it's a number, one of those branches is going to evaluate to true. If you have a number, it is either, let's leave aside, generally speaking, if you have a number, it is either greater than 0, equal to 0, or less than 0, right?
Yeah.
So they have a little note here, note 17, which again, they're just kind of talking about truthy and falsy. Right? That's the thing. And again, note 18, that's the thing about the minus operator, right? The same thing. So, note though that when you have a non-exhaustive set of cases, this is what they're talking about here. Cond has another piece of syntax. This is another way that you know that Cond is a special form, is that Cond has its own internal syntax, right?
Okay.
So we've talked about this before, but it's a point that I do want to really kind of hammer on, which is that Scheme has a very, very simple syntax, and it's got some rules, and those rules are always true unless you're inside a special form. But special forms get to establish their own syntax. And when you can write your own special forms in Scheme, and you get to establish a syntax for them. So when you see weird syntax like this, you know that it's a special form. So if we actually look at Cond here, if we look at the first line here, so we have Cond, and we have an open paren, and then the next thing after that open paren is something that evaluates to true or false, right?
Yep.
So right there, you're in a special form, because the rule is, if you're not in a special form, if you're in normal Scheme syntax, if you have an open paren, the thing that comes after the open paren has to evaluate to a procedure, right? Or it's an error. Right? If you, at the REPL, again, because of the lag, I kind of don't want you to do it, but if you were to write open paren and then another open paren less than x0 and close up your parens and type that at the REPL, you would get an error, because it'd be like, not less than, you'd get an error because it doesn't know what x is. But if you put a 3 in there instead of an x, right, and said, is 3 less than 0, you would get an error because
They expect
that would evaluate to false, and you'd get an open paren. Oops, I'm typing in the wrong place here.
Here.
And indeed, right, if you put if you put false in some parens like that, it wants a procedure, it gets false, it can't apply it, it blows up. So when you see this open paren followed by something that's not a procedure, you know that you are in a special form at that point, right?
Sure.
And special forms are very flexible in terms of what their syntax is. You have a lot of power when you define a special form to do various things in terms of this. So else is just another piece of the syntax for Kant,
Mm-hmm.
right? Which is that you can at the very end have, and it else isn't. I wonder if else. I think that. Well, I'm not going to get into it. I wonder if else truly is actually all that special here. I'm getting my lisps confused. I've written in a fair number of lisps.
Well, else is it's within Kant,
It
right?
is within Kant. Yeah.
So it doesn't.
I just have some questions about whether what they're saying here about else is actually technically true, but you don't need to worry about that. It's perfectly fine. So else just means like, okay, in this last branch, if we get to here and nothing has been true up until this point,
Yeah.
then just return this.
Uh-huh.
And you can see that that's also correct in terms of abs, right?
Well, it's less or it's negative than, and otherwise it's going to be more.
Or it's going to be 0.
Right. Well, okay. So it could be. Right. They don't have 0. They're right back. So right, you don't have the equal anymore. It's either going to be greater than, less than, or it is 0, in which case you return 0, or equal to. Well, yeah, that's kind of
right. So if x is less than 0, then negate x and return that. Otherwise, it's just x.
Yeah.
Right. That's another definition of absolute value. And so in this case, they don't have to worry about being exhaustive in their cases. For abs to be correct above, they had to be exhaustive in their cases. Right? Like one of those cases had to be true because we know that we want abs. If you give it a number, we know we always want it to return a number, right?
Mm-hmm.
And a cond that isn't exhaustive can return undefined, and undefined is not a number.
Mm.
So it would be a problem if our abs could return undefined.
Yeah.
Right? We want to know that it returns a number, and that means that its cases have to be exhaustive. But here they can write it without exhaustive cases. This is kind of exhaustive because it's like anything with an else is basically exhaustive, right? Like,
yeah, because it cleans up all the sloppy stuff.
Exactly. You're like, okay, if none of those things are true, then just return this, and boom, okay, that gets you that thing. And this is something where not just with Kond and whatever, but just in general in programming, being exhaustive in terms of your case analysis is often very, very important. And this is a place where bugs creep into people's code, which is that they fail to actually consider every case. And this is just one example of it, but this is something that comes up a lot, right? So here they're introducing if. And we've already seen if. I introduced if first because I feel like if's a little bit simpler, and it also has simpler syntax. Cond is a little bit harder in terms of just like getting the parens right. And I find it particularly confusing because, like, again, this is this thing about switching between lisps. Different lisps have slightly different rules for the syntax of some of their special forms. For instance, let is another one, and we looked at let, and I always have to think about it for a second if I'm in Scheme, because let has more parentheses in Scheme than it does in some other lisps that I'm used to. They do the same thing, it's just got slightly different syntax. So we can keep going a little bit here.
So if,
or we don't have to if there's something here you want to see.
Well, no. Let me just think about the if thing here for a second. It's not immediately making sense to me. So basically, how does it know what to return? So
Well, it's just like the if that we've seen, right? It's like
if
x is less than 0, then evaluate the first branch and return that. And evaluate to that, right? So if x is less than 0, negate x. Otherwise, just x.
But this is an if with 3 branches.
No, it's not. It's got its test, which is x is less than 0 is its test, right?
Okay.
That's the predicate, right?
Yeah.
Then the first branch is minus x, negative x, right? And then the second branch is just x.
Okay, so less than true, and then and then we get the and it would be false if it was like less if x was 0. X would not be less than 0 if x was 0.
So it would return x, and the absolute value of 0 is in fact 0.
Yeah.
Right.
Okay, cool. I got it.
So they're talking about logical compositions here, and or, which we've seen. And of course, do you remember not?
I don't remember not.
Not turns false into true and everything else into false, basically, right?
Okay.
Okay. It negates the logical sense of a truth value, right? So true becomes false and false becomes true.
Okay.
Much like
I don't see that on here.
Politics. I don't know. I assume that they'll give it if you keep going. Right? They're saying and or. Yeah, there we go. Right. It's just these. I kind of knew it would be there because these three things go together: and or and not. Use these a lot because there's a lot of times when you have like compound conditions. You're like, well, if it's Tuesday and it's raining, then this, else this, right? But sometimes it's like, and not is used. Like, let's say you have a procedure that tells you if it's raining. It's called is raining, right? We want to know if it's Tuesday and it's not raining. You could say if and is Tuesday not raining, right? So we would take the and of is Tuesday and the negation of is raining. Do you see that?
Yeah.
Okay.
Yeah.
And you can nest these things, right? You can have ors nested inside ands. You can say if, if it's Tuesday or it's raining and my dog's name is Fred. I mean, I don't know what that means, right? But like you can test for all of those things at once if you want. You can build these compound logical operators up arbitrarily in terms of how complex their nesting gets. And there's some rules we'll talk about at some point called De Morgan's laws, for instance, that are kind of useful to know. You probably know them intuitively already. But for instance, we'll talk about De Morgan's laws. I don't quite want to get into it right now. If I could type on your screen, I would right now, but otherwise, yeah. It's not
Fair enough.
So,
notice that and or are special forms, not procedures. Some expression, not necessarily all value. Right. Not as an ordinary. Not is not a special form. It's just an ordinary procedure.
Right, because you don't have to short circuit evaluation there. Not only takes one thing, and you have to evaluate that. So it doesn't have to be a special form. It doesn't have special syntax, and it doesn't have to control the evaluation of its arguments. Right.
Yep.
And so they define greater than or equal, which is built into Racket. There is already a greater than or equal in Racket. But if there weren't, you did have greater than. Note that if you have greater than, you can write less than if you want, right? Because it would just be not greater than.
Okay.
Right?
Yeah.
And you can write greater than or equal here by using or greater than xy equal xy, right? Oh yeah, and they're using a not there as another way of doing that, right?
That's not less than.
Yeah.
Cool.
But yeah, let's see. I'm just looking at the time, 10:40. Well, let's just keep going a little bit. Let's just look at what they have here. Because I think it would probably be valuable for you to go over this. Maybe even try some of the exercises if you get some time during the week.
Yeah, right. I will. This last week was another one of those, but it's this week coming over better. I mean, it's Thursday, so I've got the weekend to be able to get some stuff and spend some time in it this weekend.
Yeah, I mean, I will say, I think you're doing pretty well with a lot of this stuff conceptually. Again, a lot of people struggle with recursion, so I suspect that if this is something that you wanted to devote some time to, I suspect you'd probably be pretty good at it.
Yeah, right on. Yeah, no, I mean, I definitely. I mean, it's interesting, so I think it'll be fun to spend some time on and see.
Yeah, think we're pretty close to the point where we can start writing some programs that do things, right? I wanted to like establish some, kind of establish a little bit of a conceptual framework for some of this stuff and give you some tools for stuff. But Racket has some kind of cool little libraries for both making images and then making animations out of those images and even making little interactive things involving those interactive programs where people can interact with the mouse or the keyboard and stuff with that. And I think it'd be probably it'd be kind of fun to do some stuff with that and write some actual programs that do things. Because right now this all just seems kind of abstract. Well, you can do all this stuff, but how do you put that together into a program that actually does something, right? And that should definitely be sort of the next step. But we can keep coming back and adding more sort of tools as we go. But yeah, why don't you keep scrolling a little bit? Let's see. This is just some exercises. They have interesting names for their theoretical students here. Ben Bitdiddle.
And Bitdiddle, yeah.
Yeah. Elisa P. Hacker. That's another one of them. There's several. Some of them are smarter than others. Ben Bitdiddle, I think, is the dumb one. Yeah, so we haven't really directly addressed applicative order evaluation or normal order evaluation. I've just sort of explained that like things get evaluated before procedures get called. They talk about that in a little bit more depth, though, and I think it would be useful for you to look at their section on sort of application and substitution, right? It's implicit in a lot of what we've talked about, but they make it more expressive. But this exercise won't make sense to you without reading that section. So let's just keep going. So 1.1.7, this is kind of where things get a little bit trickier. And I'm kind of wondering if we want to like jump into this at 11:15. And I'm kind of thinking that we don't. I think that we should, though, the next time. And you could even try reading this at this point. I will say that I think it gets a little tricky. Like, if you scroll down a little bit, right, they're going to talk about, right, just because you have to kind of understand Newton's method here, which is fine. I just don't think 15 minutes is really enough here. But why don't we jump back into Racket?
Cool.
And this whole thing that they do with Newton's method and with like really abstracting stuff is actually a really, really useful section. I think it's very illustrative. SICP is a good book.
Nice.
So
yeah, check it out.
So a lot of programming languages have a function called range, a procedure called range, and Racket does as well. And I think it'd be interesting, though, to sort of make our own range function. So although it's not going to do quite as much as, it's not going to be exactly the same as Racket's, just because they're doing some stuff with arguments that we haven't seen yet. But if you type in, so range is a procedure, try doing range 10. Apply range to 10. Right.
Mm.
Okay. Now apply range to 10 and 20.
Between the two.
Yeah, but note that it doesn't include the last value. Just as when you gave it the 10, it included everything up to there. And this is actually really common, this kind of thing in computer science, where when you have like sort of two numbers, a range of things, it includes the first one, but goes up to, but not including the last one. And note that it gives you, if you just do range 10, it gives you 10 things back, right?
Yeah.
There are 10 digits. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the same thing with range 10 and 20. 20 minus 10 is 10.
Yeah.
And you get 10 things back. But because, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah.
So let's talk about just the case. Let's talk about the case where you just give it one thing.
Right.
Okay.
Yeah.
So maybe call it like my range 1 or something. right? Let's see if we can write this.
So range.
So what's its type going to be?
I mean, I'm kind of thinking about when you give it just one value, that it returns a list of values between 0 and that value.
That is correct. Yep, that's exactly what it does.
And if you give it, and then it can, and you can give it 2 values, but you can't give it more than 2 values. I can't imagine. They return a list between.
Well, I think actually, let's see. I have to.
Because it just seems like that would be.
So you can give it 3 values, but the third value has a special meaning. Why don't you try that out? Try doing range 1022. Just so you know what Racket's range is. This is why I was saying we're not going to write a range that does everything that Racket's does.
Wait, what are you saying? Range 20?
1020, 1020, and then 2. Give it 2 as the third argument. It's telling you how many to count by.
Oh, interesting.
That's what its third argument does.
That's fun. Cool.
Yeah. And this actually turns out to be pretty useful in a lot of cases. There's range actually gets used a fair bit. It's not just sort of
it's not a party trick.
Yeah, it's not just a party trick, right? It's actually range turns out to be quite useful.
All right, cool. So range is a procedure that's applied to a value that returns a list or multiple.
Okay, but what type of value? What type of value? So we're going to write a simple one. This is why we're calling it my range 1. We're going to write one that takes a single value, right? So it's going to count from 0 up to 1 less than that value, basically, right?
Okay. So it's
just because we haven't seen yet how to write functions in Racket that can take differing numbers of arguments, right? Note that range can take 1 argument, it can take 2 arguments, it can take 3 arguments. It can't take 0 arguments. That's an error. And we've seen other things like that. And is like that. Well, those are special forms anyway. But like plus is like that. Plus can take a variable number of arguments. But we have not seen how to do that yet. And I don't want to get into it right now. So let's do the simple case, which is range counts from. We can also do we'll call it. We can look at both of them. But let's do the simple case where it just takes a single number and returns a list with those integers. So its type it's a procedure that takes a number, takes a positive number, right? Let's not worry about error cases either. It's just we assume that this is going to take a positive integer, right?
Mm-hmm. Do I need to?
Well, what's the proc in
there? It's the range procedure. I mean,
we're writing the range procedure.
Okay.
Right. So this is going to have the signature that you typed in at the REPL. We had to pass procedures into map and filter because the user had to supply a procedure as part of that. That's part of the signature of it. When you call map, you give it a procedure and a list. When you call filter, you give it a procedure and a list. So that had to be part of the argument list. But for range, people just give us a number. That's what it takes. They give us 10. We give them back their list. Yeah. And, you could name that X is okay here. You could also name it end, though. Giving arguments like descriptive names is often a good thing. Because especially when we get to the 2-argument version of it, we'll probably want to call it start and end, right?
All right.
And of course, it's a little bit of a misnomer here. End almost implies that it includes that number, and the result doesn't include that number of what we're doing. But anyway.
Right. But it stops the I'm thinking about it between 0 and the number, so it is the number that stops the range counting, I guess, if that's the word. Looking at all of our.
Actually, I'm realizing something here, which is I don't think, given the time remaining to us, I don't think I
Yeah.
actually want to do this because this does get a little bit more complicated. We would have to define, like, this would be a really good thing to do if it were not 8 minutes of 11. So you know what?
Yeah.
Let's jump back over to SICP and let's just start looking at that. Like, we'll start dipping our feet into that a little bit, and it'll just kind of get us, ready for next time.
Works for me. Gotta go back up to some previous stuff.
No, let's actually just start looking at this. So, are you familiar with Newton's method at all? Well, scroll back down to where we were. Scroll back down to, is it 1.7?
Yeah, there's a lag. I'm back there.
Yeah,
I was
okay.
one up there.
Yep.
No, I mean, not that I can recall. I mean, it sounds kind of familiar, but I can't remember.
Okay, it's a method for finding the roots of equations, right? Which is, so when you the roots of functions. So I imagine that you graphed functions at some point in your past, right?
Yeah. Very, very vague. Yeah, I kind of remember that.
So when you graph a function, like if I graph, say, the square of x, right?
Mm-hmm.
I would write it out on a grid. I'd have, one line vertically, and that would represent the results, right? And I would have one line horizontally, which would represent the inputs, right? So square takes a number and it squares it. If you give square 1, it gives you a 1. If you give square 2, it gives you a 4. If you give square 3, it gives you a 9, right?
Yep.
So if you drew a curve that passed through sort of all of those points, right? And you can square things that are, you can square 1.5 as well, too, right? You get a nice, smooth, continuous curve where any point on the x-axis that you picked that represents a number there, if you went up above it, you would hit a point on the curve that was horizontally across from the point on the y-axis that x squared equaled.
Yeah.
Yeah.
Yep.
It's.
I know what you're saying.
I've been awake for a while. I'm not being super articulate here. Okay, so.
Yeah, I mean the curve has both an x and a y value. That defines what the square function is accomplishing or whatever.
So one interesting question that you can ask about functions is where do they take on the value 0? Right? Where do they cross the x-axis? So with square, that's really easy. You can figure that out without having to really do much, right? At what value does square take on the value 0?
0.
0, right. But finding roots of functions is harder for some functions than it is for square. And it's a very useful thing to be able to do. Anyway, and so that's just sort of some background. So they're talking here about finding square roots because, we all kind of know what a square root is, and we can all sort of figure out square roots in our head for easy things. But if I ask you, say, the square root of 8.6, right, it's not a tremendously easy thing to do, right?
No, I can get there.
Get there. So the question is, how do we actually calculate square roots? And that's what they're going to be talking about here, right? So they define square root there.
We asked the computer to do it.
Yeah, exactly. But if you're the person having to teach the computer how to do it,
yeah,
right. So, we talked about this with the recursive stuff, which is that, when we write recursive functions, we're essentially writing down definitions. But we're writing them in ways that the computer can actually perform, right? Mm-hmm. That's what I was saying before about how these recursive definitions are not tautologies, right? So they've given a definition here, but unfortunately this definition is not actually that they gave. It's fine for a mathematician to say, okay, that's what the square root of x is. But that thing right there, the square root of x is y such that y is greater than or equal to 0 and y squared equals x. And what they're pointing out here is you can't just write this here, what they're writing. That doesn't make any sense, right?
Yeah.
It's a tautology, basically. It is not a procedure for actually calculating square roots. And so we want to figure that out. And they're kind of talking about this here. The contrast between functions and procedures is that, you can describe the properties of things, which for a mathematician is often enough, right? A mathematician can often operate with things that have definitions without, sometimes in cases where, there's some math that involves things that we can't even figure out exactly what they are, but we can say, well, it has these properties, and therefore we can still work with those mathematically, right? But computers really do need procedures to calculate things.
Yeah.
So they're just talking here about this, and we'll take a look at this. But, if you scroll down a touch, this is a way of calculating square roots. And basically what it's saying is you guess at the value. And then you average your guess with the number you're trying to take the square root of over that guess, right? So then they give an example here with the square root of 2. So we're going to guess that the square root of 2 is 1, right?
Okay. That's the quotient part there, or that? No, it's the average. Oh no, I'm sorry. Yeah, there's the guess column right there. I'm getting that.
This result here, this 1.5 at the other side, that's our better guess, right? That's, we get to here and we say, this is a better guess for it, right? Because what we're doing is we're making a guess and then we're repeatedly performing something that improves the guess every time we do it. But it takes the new guess in on every step for the means of, right? We have something that takes a guess and improves that guess. So we make a guess to just start with. We pass it through the thing that improves that guess. We get a new guess that's a little bit better. We pass it back through the thing that improves guesses. We get a new guess that's a little bit better. And we can tell how close it is to the answer, right?
How do you know how close it is if you don't know what the answer is?
Well, think about it this way. So let's say that you say to me, I want you to calculate the square root of 2 for me, right? And I give you 1. So if you look back up at the definition of square root, right? I can multiply, right? I can multiply 1 by 1. Let me think about it this way. So if we're talking about the square root of 4, right? Mm-hmm. Let's say that I guess 2, which is exactly correct. Well, then I can multiply 2 by 2. I can square the guess and see how close it is to what I was trying to take the square root of. In this case, I know it's perfect. The difference is 0. But let's say that instead I had guessed 1.5, right? So if I square 1.5, whoops.
2.25.
Right. So I'm like, that's not a great guess. I mean, it's 1.75 off from what I was trying to find the square root of, right? Mm-hmm. So then let's say that I guess 1.8, right? 3.24. Well, that is closer to 4. So I know that 1.8 is a better guess than 1.5 was, right? Mm-hmm. Right. And what I can actually do here is I can say, let's try to keep improving this guess, right? We have this way that keeps improving it until it's within this much of what we want, because we're not guaranteed to ever actually hit exactly the thing. And particularly the square root of 2, I think we talked about this, right? The square root of 2 is irrational.
Yeah.
Which means that you can't exactly represent it in a computer anyway, right? So you're never going to get the exact correct result calculating the square root of 2. You just get something that is close enough. So I can say, well, what's close enough? Well, I could say close enough is when my guess as to the square root of 2 squared is within 0.001 of 2, right? So it's somewhere between 1.9998 and 2.001, right? Mm-hmm. And yeah, it's 11 o'clock, so maybe we should just
All this guessing stuff is Newton's method. He was just walking around guessing.
just guessing. Yeah.
Jeez,
Jeez.
I could do that.
Yeah.
Huh? That's
So,
interesting.
and this is a special case, and they go into actually doing the general case of Newton's method. The general case of Newton's method is about finding roots. It's about finding places where functions take on the value of 0. But this is a special case of it. And what you basically do with your guesses is you take the guess and you divide the thing you're trying to find the square root of by the guess,
Yeah.
right? And then you average that. Then you average that quotient. You average that quotient with the guess, right? So you can see what they're doing here.
Yeah, it's a little bit more.
Yeah.
It's definitely.
We'll talk about it next time. It's a little bit, you have to kind of like work your head through it a little bit.
Yeah, it's fine. I mean, usually when I do it, I just do the guess and then I multiply and then I. But maybe I am actually. I don't think I do the averaging because that's what I do when I'm trying to
Right.
figure something out.
This is a way of just very consistently refining,
Right.
refining the guess and making it better. So
I'll be. This is a good. It's a bit of a hanger because I'm
it's
like,
a good cliffhanger. Now you're like, wow, what do we?
how is this going to apply to a computer? It doesn't seem like the way that a computer would operate. Making guesses. I don't think of a computer as a guessing thing, so it'd be good to find out.
Well,
and I gotta
but
go.
think about it in terms of this kind of thing. We don't know what the answer is, but we can pick some guess. The guess doesn't have to be very accurate, right? We just always pick the same number if we want as the guess. But if we have a way of making guesses better, that's
Yeah.
guaranteed to always make the guess better, then we're guaranteed to be able to keep getting closer to it. And
Nice.
indeed, if we do it enough times, we're pretty much, well, all right, now we're starting to get into infinite series, and that's actually not really true, but you kind of think, well, maybe we're guaranteed to be able to get within this close of something.
To get
Sometime.
good enough. There's something somewhere is going to be good enough.
Yeah,
Yes.
but that isn't really necessarily guaranteed. For instance, if I add up an infinite number of terms, right?
Uh-oh.
For many sequences, if I add up an infinite number of things, for instance, if my sequence is an infinite number of ones, then I'm going to get infinity, right?
I guess so.
It turns out that there are infinite series of things that you can add up that don't go to infinity,
Yeah.
that sum up to 1, right? They just keep getting closer and closer and closer to 1 without ever actually reaching it. But then we basically say that if you add up an infinite number of those things, then that actually equals 1. So you're not actually guaranteed by doing something like this. As why I was kind of saying, there aren't actually guarantees about this. But I think in this case, the case of the square root and Newton's method, we are guaranteed to keep getting closer to the correct answer. Right? It happens to be a property of this particular case.
Yes.
Anyway,
Cool.
so
Yeah.
we'll talk next week.
Very good.
All right. Have
All
a good
right.
one, man. Bye-bye.
Thanks. You too. Bye.